it at the back? Yeah. Okay, well, welcome back from lunch. As you can see, we've been joined by a few people. So we've got a number of people, as I think the students already know, and everybody, of course, here already knows, this is the 10th Heliophysics Summer School. And so, supported by NASA. And so as part of this, we have organized a celebration of that. And to know a little bit about the motivation and the history of the summer school, and then closer to the end, some projections into the future, which I'm going to actually ask the students to be involved in, since they are the future of the field. So to start with, I've been asked, there's a panel about the motivation of the summer school, and I've been asked to introduce somebody who I know fairly well, but whose name I have trouble pronouncing, somebody whose name I can pronounce, but I don't know very well, and somebody who I know and can pronounce their names. So, so here goes. And actually, I have notes even that I wrote down, so I want to get those out. And so, first, our panel that got together more than 10 years ago somehow and cooked up the idea about having a summer school and the importance of that for the community. So to start with, Madhulika Gohatakota, who I've only ever just called Lika, but maybe but Carl has been tutoring me. And at the time, Mandalika was led the Living with a Star program out of NASA. Currently is a heliophysics scientist at the Goddard Space Flight Center.
And at headquarters.
At headquarters. I'm sorry. And to her right is Dick Fisher, who just described himself as to me, and allowed me to say this out loud. He described himself as a high-mileage, thin-threaded astronomer. But at the time, he was the director of the Sun-Earth Connection Science Division at NASA, which has now been the predecessor to the Heliophysics Division, and is currently Scientist Emeritus at Goddard. And then Meg Austin is was the director of VSP, is the director of VSP? There's some reorganization going on.
Reorganization, combining of programs.
Okay. And, but also then, of course, was instrumental in supporting the beginning of the program and organizing the first sets of summer schools, and continues to organize the sets of summer schools. So I'm going to turn it over to them now. So who's going to start?
I'll start.
Excellent.
Thank you so much, Nick. And Nick has played actually a vital role in the summer school in actually bringing, along with the teaching material, the labs where students can actually experiment with the theoretical ideas and get some excitement out of it by tweaking parameters and understand the regimes that they are working in. So good afternoon to all of you. It's a pleasure being here. It's a pleasure actually sort of, in a way, ushering history. This is, to me, a history-making moment, but you can't talk about history when you are in the present. If you think about meteorology, as a discipline, as a world, I don't know what 50 years ago looked like. Well, we are kind of like that. In heliophysics, we started a new discipline. How many of us can say that, right? Kind of being at the beginning stages of a new discipline. And of course, what we are going to share here is, nothing too preachy, some information. And it's going to be his story or her story. I will start with her story, but you're going to hear different versions of how heliophysics came to be. And like Hillary Clinton said that it takes a village to raise our children. I think it takes a community, all of you, and even more, to have created this discipline, and it will take that same amount of momentum to keep this going for the next solar cycle. So with that, I'll kind of give you a version of my story, how I got involved in this. I never in my life imagined that I'll be playing a role in something that is going to be significant. So how did it all start for me? 100 years ago, the Sun-Earth connection was of interest to only a small number of scientists. Solar activity had little effect on daily life, and this is a long time ago. Today, a single strong solar flare could bring civilization to its knees. Modern society has come to depend on technologies sensitive to solar radiation and solar storms that lead to geomagnetic storms. And all of you are very familiar with that today. And it was during this realization that the Living with the Star program was born at NASA headquarters, still under the Sun-Earth Connection Division name. And I was the lead program scientist for it and continued for the last 15 years. And the way this program began was with a very simple question. And the question was, why do science? And what I'm going to show you here is a chart that kind of really epitomizes the program within heliophysics from Donald Stokes from Woodrow Wilson School for Public Affairs. Let me see if I can go back to my original slide. And the question, so why do science? And so Donald Stokes kind of put this on two axes. All research can be plotted on two axes, curiosity versus utility. And that's what you're looking at. The result is three distinct classes of research. Pure basic research, exemplified by the work of Bohr. You're familiar with him, early 20th century atomic physicist. Pure applied research, exemplified by the work of Thomas Edison, inventor, use-inspired basic research. And then the kind of science that LWS came to be, it's a unique science that is kind of put in the Pasteur quadrant, which is the kind of after what Louis Pasteur did, right? It is an equal mix of curiosity and utility. And that's where Living with the Star program resides. So it has both application and it also has fundamental science embedded in it. And then to speed the application of the research that was carried out under the Living with the Star program, we started what's called LWS Institutes here at UCAR, pursuing this work into the Edison quadrant so that there is greater utility and application. And examples are that are, of course, ground-induced current, transformer heating. They have real meaning, real application. So what are the societal consequences of solar variability? And I'll just go over it very quickly because you're going to hear more about it. Human radiation exposure. We have been living outside of our low Earth or outside of our lower atmosphere in space for a long time, over a decade in space station. Space exploration and utilization of the large-scale solar system that's going on. And it's not just with human astronauts, but also with our robotic spacecraft. High-altitude flight and aviation are just as susceptible to radiation. Then impacts on technology, that's a huge area that has unfolded, as our vulnerability to solar radiation has increased with our dependence on technologies, space systems, communication, navigation, ground infrastructure. If there is anything that is electromagnetic in nature, you can bet that it can be affected by solar storms. And finally, terrestrial climate. Nothing is outside the realm of the heliophysics, living with a star program within that. So both short-term climate and long-term climate are essentially modulated by solar variability, by total solar irradiance, by spectral solar irradiance. This chart kind of tries to tell us that this whole notion of space weather only during solar maximum is not the right way to look at space weather. Space weather actually happens at all phases of the solar cycle. In some ways, we've just seen the weakest solar cycle of the past century in the last solar cycle. What's next? We are still trying to understand. During solar minimum, solar activity does not vanish, it just changes form. And so it's kind of cute. Solar El Nino and solar La Nina are two sides of this great climate oscillation, not on Earth actually, but on the sun. And this sideways solar cycle kind of gives you a picture of all the different space weather impacts that happens during both the low sunspot number and the high sunspot number. If we want to explore deep space, we don't necessarily want to go there during solar maximum, but maybe during solar minimum or an optimum time, because during solar minimum, when the solar magnetic field is weak, the galactic cosmic rays can invade the solar system. And that could be much more lethal, not only to our astronauts, but probably to our space system. Not going over this, but you're already familiar with it. It is just kind of looking at it differently as opposed to an XY scale of solar variability. It is a representation of solar cycle as two extremes. And now, today, we are actually sort of in a new paradigm mode. At the dawn of space age, more than 50 years ago, protecting ourselves meant protecting our assets on Earth. And that is no longer the case. Our domain has increased significantly. We have spacecraft at Mercury, at Pluto, at Jupiter, and we are actually teetering at the boundary with our Voyager spacecraft leaving the solar system itself. In some ways, the pasture quadrant that I showed you earlier just got bigger than Earth. It encompasses the whole solar system. And what you're seeing there are representation of the power of our theoretical modeling tool with assimilation of observations, and that's a model which can predict solar system elsewhere. So Sun-Earth system science just kind of grew from being a consuming science where we took resources from taxpayers to do our curiosity-driven science to a producing science for the benefit of humankind. Space weather is no longer the domain of Earth only, as depicted by the beautiful aurora. Space weather is now also interplanetary, and we are learning this every day with the interaction of solar wind, solar radiation with other planets with strong magnetosphere or strong ionosphere. You'll hear more about it later in some of the talks. But more interestingly, space weather has just become exoplanetary in nature as well. Scientists are actually beginning to use the concept of sun as a star and Earth as a planet, but taking it into the domain of stellar astrophysics. So just having a star in a Goldilocks zone or a planet in a Goldilocks zone doesn't necessarily mean that life can evolve there. You also have to understand the interaction between that star and that planet. And so this is kind of space weather in extreme environment. That's our red dwarf being simulated there, where you can see the spots on this star is sort of covering 50% of that stellar body, and kind of the space weather conditions it generates is ripping off the planetary environment of that exoplanet. So that exoplanet could be in Goldilocks zone, yet would not be able to support life. But all of this is coming from the research that we are doing in fundamental heliophysics, trying to understand the connection between our star, the sun, and our planet, the Earth. So NASA science, I just want to show, and I talked to the students earlier, that it is really very interconnected. And there are like 3 profound questions that all of our science is trying to address: heliophysics, astrophysics, planetary science, and earth science. And those questions are, is life sustainable? Are we alone? Habitable worlds. And if you look at kind of the connection there, you will find that our 4th book, Comparative Heliophysics, kind of will touch on all these areas. So science really is very integrated. And so now, a new science needs new scientists. And that's how Heliophysics Summer School came into being. You know, being the name of a NASA science division, Heliophysics did not guarantee that heliophysics will be a discipline. But when you have actually created new interdisciplinary scientists and created new textbooks, that concept is not going to go away. So funded by NASA and managed by UCAR, the first Heliophysics Summer School was convened in July 2007. The deans were George Sisko and Karel Schreiber, and 35 young scientists from all over the world were actually instructed by 23 experts. And today is the 10th year of that. And we have trained over hundreds of young minds during this time frame. And graduate with extraordinary promise, they compete for and receive Jack Eddy Fellowship, sort of early career postdoctoral fellowship named after Jack Eddy, who was also here at NCAR, UCAR, a pioneering researcher in solar physics who shaped thinking about the sun-earth connection in the 20th century. These fellowships provide the support they need to continue their studies as heliophysics postdocs at leading universities. Later, some Jack Eddy Fellows returned to the Heliophysics Summer School as instructors, and you will hear feedback from some of them. So Jack Eddy Postdoctoral Fellowship Program was established in 2009. Today we have 23 Eddy Fellows. And remember, these are students, early career scientists, who are now interdisciplinary scientists, and those are the pictures of those young early career interdisciplinary scientists. So this is the best way I could put it, sort of what have we achieved here? It is the whole heliophysics life cycle. We have created 5 heliophysics textbooks which give academic form to this new discipline, laying the groundwork first, given that we were creating the first comprehensive reading and teaching material for heliophysics as an integrated discipline, which grew out of adjacent, largely independent, evolving scientific disciplines. And that's what we succeeded in doing over the last 10 years in 5 different textbooks. And what are the summer school students? They are sort of the caterpillars that enter the cocoon of the summer school and emerge as beautiful heliophysics butterflies. And Jack Eddy Fellows are the monarchs. And I will end on a personal note, a monarch from a previous generation. So what you're seeing there, I was also a student here as a graduate fellow at High Altitude Observatory, a picture I was stunned to see myself, which came about during the 75th anniversary of HAO. That is 1983. In the middle, what you see, and you see my esteemed mentor and also my boss for a long time, Dick Fisher. There is Tim Collin, who was here, I think, head of NCAR at that point. You see Tom Bogdan, who's been UCAR president. And we were signing the first MOU in 2005 to really figure out how to bring scientists together under one sort of umbrella. And HAO NCAR provided that facility for the focused science teams to come interact. That was sort of the beginning before we kind of went into establishing the Heliophysics summer school. That picture there is essentially from 2007. That is the first summer school. I'm going to play this as we are doing this. And you can see that is evolution of sort of my own career, my life. You know, I led the Living with the Star program, Solar Dynamics Observatory, Van Allen probes. That's kind of revolutionizing the Sun-Earth systems understanding. And what you see here is the last mission that I led, Solar Probe Plus, I would say. That is, again, humanity's first voyage to a star. You know, we have gone as far as Pluto, to the outer boundary and moving away from the solar system. But Solar Probe Plus is going to define, again, an history-defining moment when it is going to go to within 10 solar radii of the sun to gather the observations, I would say, ground truth validation that we need in order to move forward with heliophysics. Thank you. Dick?
I don't hardly know where to start. Lika was very complete about the whole thing. I guess one thing I'd point out is Andy would know what meteorology looked like 50 years ago. We can remember pretty well, I think, sort of what it looked like. I'm only going to make, I'm going to issue a warning and then I'm going to make one remark. The warning is that what I have to offer is narrative. It isn't actual real history. And the problem with narrative is it comes from the viewpoint of a single person. And when you are involved with things like flying, playing golf, fishing, things like that, basically it's difficult. You get narrative about that. And there's another activity in humans get into, which are fairy tales. And so I would give you a little formula to use as you're listening to the narrative. Fishing stories, golf stories, so forth and so on, always start with the words, "You aren't going to believe this. But I was right there, and this is what I saw." And the fairy tales always start out a different way. Once upon a time, a long time ago, in a galaxy far, far away. But past that point, they are all virtually the same. So just keep that in mind. Now, I have only one story to tell about the summer school, and that is in the early part of 1997. I was concerned. I had a concern. My concern was that we didn't really understand where I was working, how to build instrumentation very well. It was a thing which was difficult to execute. It was not that it wasn't built well. It was that the execution was sort of labor intensive, and it kind of used people up, or used me up anyway. And I thought, well, the only hope for this is to follow a model that was used in the late 19th century by a man named Abraham Fluxner, who revised medical education for the world in about 20 years. And it was a paradigm shift point because Pasteur had changed medicine from a situation where you treated a patient to where you could actually cure a patient. Now, Pasteur, of course, and Stokes was well aware of this, didn't start out that way. What he was after was a simple thing, which was, how can we make better beer? That's a good societal question. So I was hoping, how could we avoid all the extra energy we're putting into building instruments at the institute where I was working, NCAR? And to do this, I had encouragement from the HAO staff and support from the institute itself, from the advanced study program, to have a summer institute entitled Astronomical Instrumentation in the Field of Solar Physics. And taking Flexner as a model, my conclusion was that what we had to have was high context, high volume. So what Flexner did was he essentially inculcated medical education into a teaching hospital. So you went and you had to change diapers and you had to administer to patients who were suffering and so forth and so on, but you also had to learn a lot of academic stuff and a lot of high volume. So we had our little summer school, and we had things where I got a lot of cooperation from the community who just backed like crazy. And we got people who had built stuff and were building stuff that was obvious importance to the nation and the national effort in what would become the Sun-Earth connection. And they came and lectured. There were also exercises to try and help people think through systems design. These were things like, how many wires are there going to be on this box and where are you going to route them, so forth and so on. And then we had a road trip, and we had a lot of fun on the road trip. We went to all the big observatories in the Southwest, and we also visited places where they were making hardware for space. Now, the point of this story is in the future from when we all departed. There were only 16 students, and there were 2 extras. Lika was one who said, I'm going to go to this, whether you like it or not. And I went, of course we like it a lot. And I don't remember, were you on the road trip? Part of the road trip, I think. And the other was a chap named Hassler, who has gone on to be a principal investigator. But at any rate, of these students, I changed jobs in 1990 and went to NASA. And in the sort of the height of the Soho era, 1995, 96, 97, on down through there, it turned out that working around me in the Institute were 7 of my former students. And it convinced me, I had been only an academic once, and I never could tell whether it was doing any good or whether people liked it or whether it was successful or not. And this convinced me that it was possible to change the landscape with people who had talent, who had a lot of desire, and had real concern for the integrity of the enterprise. And I completely echo Lika's thoughts about the most important people sitting in this room are you who are participating in the school, because you are the ones that will have the opportunity of taking this forward if it's meritorious and requires more work and is worthy of taking forward. So that's my story about how we got started on the road to a summer school. And you'll have to, and so like all good fishing, fairy tale, space flight, flying stories, there are 3 elements. First of all, there's a separation, then there's a struggle, and then there's resolution. And for me, this is enormous resolution to be invited to see this today, because I didn't know how it was going to turn out. So thank you very much.
So Lika asked me to say a few words to you about how the UCAR Visiting Scientist Programs was motivated to partner with NASA Living with a Star to support the summer school. And there are really 2 primary reasons why we decided that this was good for the science community that we serve. And the first is that the summer school and the associated activities, the Jack Eddy Fellowship Program, and more recently the Living with a Star Institute, fit within the Visiting Scientist Program's mission. And our mission is one of our missions is to train the next generation of scientists needed to work in specific new areas. And so this was very exciting for us to broaden our support to become more involved with this community of scientists. And the second motivating factor for me was the opportunity it provided to partner with Lika. Lika is a respected and accomplished scientist at NASA who's both brave and creative in approaching her work. And I love her style. And I have greatly enjoyed working with you these past 10 years as we've built this program together. I also want to thank George Sisko and Carl Schreiber the founding deans who crafted the concept paper that we used when we submitted our initial proposal to NASA for this program, and to all the deans that are here today who have given their time to the school over the years. I know how much work it involves. And I also want to thank Nick Gross and Tony Phillips, who's not here, for their contributions to the program over the years. And finally, to the Visiting Scientist Program staff, who have supported different elements of all of these different activities throughout the years. And especially one of the staff members who's here today, Suzanne Demara, if you would raise your hand, Suzanne. Suzanne deserves a big hand. She has pretty much single-handedly designed and maintained the Heliophysics website with all the many resources that we provide to all of you. It has really been her baby in doing this, and she has also partnered with Carl and George in getting permissions for the textbooks, mailing out the textbooks, doing all of those wonderful things. And so then just in closing, I just want to say that it takes time to pull the data that we need to generate the metrics to show whether this is a useful program for the community. And now 10 years in, and over 300 students, 316 I think, right Suzanne, have participated in the school to date. And we are getting feedback now that a significant number of you are using heliophysics at your current institutions as we go forward. So very happy to report that. So thank you.
I was just going to take actually a moment to recognize all our deans. Over 10 years, we have had several, along with Nick Gross. If you could stand up so people know who you are. You heard about George and Carl. There is Jan, Dana, Amitava, and Fran, and then Nick. I mean, these are sort of the core members who have pulled this together over these 10 years. So your contribution is immense, and thank you very much. And thanks to everyone.
So the next three speakers, I don't know that we necessarily have to bring them all up here at once, but but I just wanted to. Yep. Okay. Good. So there's one thing to have a vision, and the vision is important. Actually implementing that is another aspect of that, and I think that's what the next three speakers are going to be about. So the first two speakers are the initial deans of the first summer school, Carl Shriver and George Sisko. And I just double-checked, and I wanted to, any time that I've interacted with George, George has always, since I was with SISM together and now here at the summer school, George has always been leading the charge to incorporate student activities, students actively engaged in either looking at models, looking at data, doing forecasting, and I count at least 3 different programs in which I think George's drive to have students doing something rather than sitting listening to somebody were important. So I just wanted to acknowledge that, and that sort of like paved the way for some of the work that I do now. So, but to start with, we'll have Carl Shriver come up from Lockheed Martin, formerly from Lockheed Martin, and talk about learning about living with a star. And you're there.
I hope I am.
I hope you're there. I should have pressed that first.
All right. Well, good afternoon. It really is a pleasure to be here. It's nice to see so many familiar faces and friends from around here, but it's wonderful to see all the new faces because you are the future. You are why we're having this Heliophysics summer school, and I envy you. When I was in your career phase, just finishing my PhD or beginning my first postdocs, actually my first postdoc was here in Boulder, up the hill there, I was trained as a stellar astrophysicist in stellar evolution theory, convection theory, radiative transport, all the way out to black holes and intergalactic matter. But when I came to the US, and after a few years found myself in, I guess the first thing I did with NASA was one of their strategic planning exercises, a roadmap exercise, starting to talk to my colleagues from across the fields that we now know as heliophysics. I had a hard time following their arguments. I had a hard time appreciating their priorities, their assessments of what was important and what was not, and what was right and not, and where to put things, because I didn't even speak their language. In many ways, the words we use in one discipline are different from the meaning we give them in another discipline. So when the landscape shaped itself, I'll put it that way, because you've heard in a way what Dick and Lika said about, I'll say there's no such thing as a free lunch. I was invited to a free lunch, and suddenly I found myself looking at the prospect of creating this summer school. And when you can do that, teamed up with someone like an outstanding researcher and incredibly patient teacher like George Sisko, I thought, this is worth trying to do, because it is in the interface of disciplines that you find the most important challenges and rewarding discoveries. But you have to get your mind right, set up properly in order to be able to appreciate this. So in thinking back about what I thought at the time were really the reasons why I would want to do this, I still find them valid, and I'll share them with you, and I hope you'll recognize a number of them, and I hope the presentation works. We haven't actually tried this out. But the obvious one is the one that you've been talking about all of this week. You're talking about a system of systems. All of these coupled processes that go all the way from actually the stock market, all the way to the dynamo that sits in the depths of the sun, are relevant. And if you want to understand a system, you have to be aware of the components of the system, and you have some working knowledge of the components of the system. So this one's easy. Yes, you have, in order to work on any part of a system, you have to know the context within that is operating. And ideally, you can work your way around several concepts, several of those disciplines over time, and make contributions there as a researcher. But there were three other really big reasons that I think bear making explicit. One has to do with this diagram. This is a version of a diagram that you'll find in the first of our textbooks. It's a diagram that has a ridiculous number of scales on both axes. The temperature scale ranges over a factor of 1,000,000. The density scale goes over, okay, I exaggerated slightly, 30 orders of magnitude would have been enough, but 30 orders of magnitude is a lot. So we know the world that we live in, which sort of sits in that little corner. I'll call that the mammal range. Now, that's not even where we are comfortable, because we don't swim in water all that often, and the fish, the mammals that live in the oceans don't come out into the air all that often. So really, what from everyday experience you know is even smaller than that little thing, and then suddenly, when you become a scientist in heliophysics, you go all over this diagram, and I just picked 4 of these other domains. We have no intuition there. Even as physicists, we have no intuition there. We can write down an equation, but that doesn't give you insight. That doesn't tell you what to expect. It doesn't tell you what is right in what you wrote or thought or talked about until you go there and look at it. And then you can begin to look at these different things, and oh, by the way, we're still really bad at making multidimensional graphs, because obviously the really important and interesting one that is missing is the magnetic field, for which we really don't have intuition here on Earth very much at all. So it is also about an expansion of experience. If you want to know what happens by changing conditions, look somewhere else in the heliophysics system. And I think, okay, one of the interesting chapters, all of the chapters are interesting. All of our children are beautiful. But I thought one interesting chapter that you might want to pay attention to in particular is something that Margit Kivelson wrote, where she basically says we can look at all these dimensionless numbers that we have in physics, and all we have to do is change the dimensional number from bigger than 1 to smaller than 1, or a lot bigger or a lot smaller, and something changes. And actually, if you go through heliophysics, the domain of heliophysics, you can find some situation, whether it's a moon plowing through a subsonic wind or the heliosphere impinging on the interstellar medium, that is an equivalent of that. Expansion of experience. The third reason takes a little bit of introduction. There's lots and lots of workshops and conferences in this world. You can go to 2 or 3 conferences every single week in the field of heliophysics and not run out of conferences to go to. Well, you can't. So you're sampling. That means you're subsampling your discipline, but you have to. One of those that I happened to start going to when I started my thesis was what's called the Cool Stars Workshop, although the full name is Cool Stars, Solar Systems, and the Sun. That is one of these interdisciplinary sciences in which, if you read to the bottom of this, in the 19th incarnation that just ended last month, were the first of the exoplanets orbiting an other than a solar type star, other than our own solar type star was orbiting, was announced only 21 years ago. We're the first brown dwarf, a star that isn't a star because it can burn deuterium but not hydrogen, the brown dwarf class. And we now know that these objects actually outnumber most other objects in the galaxy. I'll get back to that in just a moment. That's where you learn about the life history of a star like the Sun, from its nebula into its red giant phase, and its activity from giant polar spots to not very much at all by the time it ends its life. We also know that, I'm getting onto the theme here of comparative heliophysics, that whatever we look at here on Earth happens somewhere else. If you're interested in aurorae and magnetic storms, well, all you need to do is look at another planet, and you can compare what happens in those conditions on other planets in our own solar system. And if you're interested in exoplanets, well, as I said, 21 years ago, we knew of one planetary system. Now, statistically, we know of about 100 billion in our galaxy. I can say that number, but you cannot grasp that number. I can't grasp that number. I'll come back to that in just a moment. As far as I know, this is a screen snapshot last week. What's on this screen is actually correct, including the statement that it's a really long page. We have several thousand planetary systems that we now know and have been confirmed. We have statistical evidence that something like 10 billion planets in our galaxy float around their host star in the habitable zone. Maybe 40 billion. If you're counting red dwarf stars, which have a very long and interesting life compared to our Sun. So we've gone from few numbers to lots of numbers. The same is true in statistics on, well, we know where these planetary candidates are. You'll find the first papers that are not speculation, but beginning to be measurements of atmospheric evolution of these stars. Now with Hubble just a few weeks ago on the shot. Today, another conference starts, you're missing that one, about exoplanet climates. And this is the 4th in their series. We've gone from the single case to the few cases to, I'll repeat the word a few times towards the end, population heliophysics, where we're doing really large number statistics to distill the laws that govern all of this from the large numbers, as well as attacking it from the case study. Another theme I'll get to in just a moment. We'll see the rare and unusual thing. We've wondered about how large a flare, how large a coronal mass ejection can the Sun actually generate? Well, we could sit around for a few thousand years, or we can look at 150,000 stars like Kepler did and get fairly good statistics. And some of these stars throw out flares that are, I don't know, you probably had the flare scale, but this one is equivalent to an X 100,000 flare. These do not make astronauts very happy, and it probably wouldn't make a lot of us here using electricity very happy if that happened on the Sun. So, and I'd just like to have a visual movie here, but this is a movie that our colleagues from the astrophysics side put together. Every one of these blurry things is a galaxy. There's about 100 billion galaxies in the visible universe, and each one of them has about 100 billion stars, and each one of those stars, statistically speaking, has at least one planet. There's a lot of work for you out there. You don't have access to every one of them, But you don't have to limit yourself to one planetary system or 10 planetary systems. Soon, within a decade or two, you'll be working with 10,000 planetary systems. Each one of them has heliophysical processes going on in them. So, to me, that means that heliophysics in large numbers is about approximating experimental physics. This is what an astronomer cannot do in the lab. You cannot tweak a knob. You can't say, what if I double gravity or triple the temperature? You can't do that. But you can just look at another system and learn about that. And if you have enough systems, you're close to being an experimental astrophysicist. The fourth has to do with this. Okay. I moved, Nick said it, away from Lockheed Martin because my interests went beyond the job I had there. You might call it retirement, but I think it's a new part of my career. But I thought if I moved to the end of the Oregon Trail, which is where some 600,000 people moved a wagon across mountains, deserts, rivers, to the end of that trail in Oregon City, how did they do that? So I felt I should read something. And as I was reading it, this diagram popped up in that book. So what is that? How do you get your load from one end of the country to the other end of the country? Well, you have someone pull it for you. You could try a horse, but horses really weren't the best choice. They didn't survive deserts very well. So you can try oxen. Well, oxen were okay, except they have split hooves, and if they see buffalo roam, they go after the buffalo. So people chose mules. One mule can carry only so much behind them. 2 mules can draw more. 4 mules, you've got a problem. 4 mules you can't put side by side anymore, because then you're wider than the path is. Right? 5, 6 mules doesn't work either. And putting 2 mule teams ahead of each other is really hard to run. So people naturally gravitated to 3 mules. 3 mules in front of a bar that pulls the wagon. How do you do that? You tie them up, right? You tie them up, and the one that walks slowest is never pulling. Unless you come up with a clever system that, as long as they're all sort of pulling, the system behind it, the yoke, is readjusting so that all 3 are always tight in their leads. You recognize this? Okay, the Romans had trigas, 3-horse things that they ran 2,000 years ago. And I'm not quite sure that they had it just like that, but they figured out all 3 need to do something. Why am I telling you this about the Oregon Trail? This came just 2 days after I was reading another article about this thing, the Mars rover. Look at the wheels. 3 wheels in a configuration that always has all 3 on the ground unless there's something really wrong with the ground. And if any one of the wheels doesn't have great traction, 2 others still have traction. If 2 fail, you'll still have 1 always on the ground with traction because of that clever invention. Well, it wasn't really an invention. Well, it was an invention, but it had been made thousands of years ago. Why am I saying all of this? Recognizing analogs. If you create an environment in which you are aware of other worlds and other circumstances and other conditions and apply your science to it, you go, I know that, I've seen that somewhere, and it does that in this condition. And I think that is the 4th reason why I thought this was important to be exposed, not just to our own planetary system or the planet you work on or the star you work on, but to so many others that you will have a chance of recognizing analogies when you do this. So that's where we are, Heliophysics Summer School. You've heard a few of the pieces of how it came about. One other piece that I'd like to add is that when George and I discussed this, at the very outset, we said, this has to be a worldwide endeavor. We have to attract the best students from around the world, and we have to get the best teachers from around the world. And fortunately, we found through the visiting science program here, and its incredibly competent and beautiful support structure, the means to do this. So thank you all for doing this all that time. The authors wrote the books. All we did was a little bit of editing, and it's surprising how many emails you can spend on editing with the authors. But I'm very grateful to all the authors that have done all these things, even though as editors we gave them a hard time at times to rewrite. And you've heard the pieces of this. I'll put it on one slide because I thought I'll have it on one slide anyway. George and I think, started thinking about this in 2006. 2007 was the first goal. There was actually a proposal submitted before we could do this. Fran, Amitava, Dana, and Jan, you've seen them, they just stood up, have been involved in leading this. Oh yes, and you know how long it is and how many people there are. You'll hear more from Andres and Neil about all the students that have come through and where they ended up. By the way, one of the simulations that you were showing, that planetary impact of the coronal mass ejection, was written by someone who started here in this school in some of the first years of it, for Cohen. We have these books out. Yes, there is a fifth book. It's not printed because it's not worth printing, but because that one, the actual impacts of space weather, is a hard one to complete in a sense. And we didn't want to let its chapters age so much that they were just outdated by the time you had access to them. So it's online, but I hope it can still grow. There's all these lectures in there, distributed over all these various things, to me always having in mind these 4 themes and what I think is an important ingredient of the future. The case study is important. You should write case studies. The comparative heliophysics is interesting because you can say, what happens in that situation? But you have to get to population heliophysics also, where you do large number studies. Hundreds of active regions, tens of thousands of coronal mass ejections, thousands of planetary atmospheres evolving before you can distill the laws out of that. So I hope that whenever you step out and happen to see a sky like this, which is really hard because this was taken with a fairly big telescope, but out at Flagstaff, every one of these stars, statistically speaking, has a planetary system around it. And many of them are coming in reach. And looking down to the ground, everything you see has something to do with heliophysics. Heliophysics in the broader sense of the word. It's not just the short-term variability. It's the fact that our planetary atmosphere is the way that it is also part of heliophysics. So to me, almost the last line of this, heliophysics really is the pursuit of societally relevant science of the local cosmos, and you have the entire universe available to study it with. Well, the part that's close enough for your telescopes to reach. Now, the challenge for you all is to grasp enough of this that you can work with this, but also that you have to realize that this field is so big, it challenges its own organizational structures. It's too big to fit into any discipline, any department in a university. It's too big to fit in any branch of your funding agencies, no matter what country you happen to come from. So you'll have to always be fighting to reach out to these other disciplines and say, what I have to offer is interesting to you because what you have to offer is of interest to me. And at some point, I hope that heliophysics will expand well beyond what it is now even, and encompass all these planetary systems out there with their own atmospheres and their own habitability spheres and maybe someday life. Thank you. Do I get to go? Questions? You can ask questions. All right. We'll come back to it later. Thank you. The picture supposedly is an astronomy picture of the day. The link is at the bottom, taken from Flagstaff, the sky over the U.S. Naval Observatory at Flagstaff. Cloud over a mountain. The little dots above it are stars. What are you asking? What is it? Ah, it's a mountain? With a cloud on a mountain?
All right, thank you, Carl. Our next speaker is the other first dean of the first Heliophysics Summer School, George Sisko, formerly of Boston University and AFRL. And UCLA. Currently, not sole, but owner and proprietor of the Old Professor's Bookstop in Belfast, Maine. Is that correct? So, which I vowed to make a road trip to at the end of this summer. And which one's you? That's you. Right. And so I'm going to do that and get out of your way.
Thank you, Nick, and thanks for inviting me to participate in this 10th anniversary celebration. When Nika called, I told her I had been out of the field too long. I don't feel qualified to participate in this celebration. And she said, well, if you cover the history of the field up to the time that the summer school started, you'll be qualified, because nothing has changed in the history up to when the workshop started. So I agreed to do that, and I was dragged out of retirement. But now I can use the stuff which I'd already developed for history courses before that. I could start as far back as Aristotle, who identified 7 different auroral types and had a theory for what caused them. But that theory went away when the geocentric system was replaced by the heliocentric system. So Galileo stepped in and had another theory. And he, by the way, gave us the name Aurora Borealis. That went away too. And I could also mention that Alexander von Humboldt gave us the name geomagnetic storm around 1810 and discovered that geomagnetic storms were at least continent-wide from Britain to Europe. And the 5th book of his series, The Cosmos, brought to a public attention the fact that sunspots have an 11-year cycle. That was picked up immediately by geomagneticians who realized that they had a 11-year cycle too. So by 1850, the people knew that the sun and the geomagnetism were related. They already knew that geomagnetisms and auroras were related. So the idea of a system involving sun, earth, geomagnetisms, and auroras was already present around 1859 when it was dramatically demonstrated with the Carrington event, which was a white light flare that caused the largest auroral display that's ever been seen that we know about. But I won't, because basically all of these disjointed efforts to expose the phenomena of heliophysics weren't recognized as a science, as an integrated science. That started in 1882, when we've had the first program of international program, I'm trying to figure out how this works, international program in which one does synoptic studies, yes, thanks, synoptic studies of phenomena from over the large part of the Earth. And that started in 1882 with the International Polar Year. And 50 years later, there was the second International Polar Year. 25 years later, there was the International Geophysical Year. And then we have more. International Quiet Sun Year, 64. International Magnetospheric Study in 76. Solar Terrestrial Energy Program in 90. And this is where my history stops, with the International Heliophysics Year in 2007. The fellow who actually instituted this whole series was a fellow, an Austro-Hungarian explorer named Karl Weyprecht. And his idea was that all of this polar exploration that had been going on because people were trying to reach China by means of a route that goes over the top of Canada. So there was a lot of polar exploration. He said what we need to do is actually put together an international program to learn about the polar regions, and that requires replacing exploration by scientific study. And so he wanted to establish a network of circumpolar stations, synoptic studies of geomagnetisms, auroras, atmospheric electricity, and meteorology, and to produce a common data format. Now, what I want to emphasize here is the emphasis on the replacing exploration by scientific research, because that's going to be a theme that cuts through all of this, these international programs. I should mention that about this time, Björklund realized that, through his studies, that the geomagnetic disturbances must be caused by currents coming from the space and going back out into space again. That was a major discovery.
And he also realized that space must be filled up with charged particles to do this. He pointed that out in 1913. The next international program was the International Polar Year number 2. Oh, sorry. What did IPY-1 do? Well, they got the auroral oval structure and dynamics, currents flowing between the upper atmosphere and producing magnetic disturbances on the ground, currents flow between the atmosphere and space, and synoptic studies revealed global interconnectedness. Then we had IPY number 2. The statement justifying that was magnetic and auroral and meteorological observations at a network of stations in the Arctic and Antarctic would materially advance the present knowledge and understanding of geomagnetic auroral and meteorological phenomena, not only within the polar regions, but in general. And this increased knowledge will be of practical applications to problems connected with terrestrial magnetism, marine and aerial navigation, wireless telegraphy, and weather forecasting. Now, this is the first time you will see a reference to what we now call space weather, and it's the last time. After this, all of the international programs basically forgot about space weather until it came back relatively recently. What happened during the IPY2? Well, Silsby and Vestine did a synoptic analysis to discover that what we call magnetic bays are well-defined distributions of currents in the ionosphere. The idea was that these things are just sitting there all the time and the Earth rotates under them and gives you magnetic bays around midnight. And Chapman and Ferrara discovered that, or at least theorized, that the geomagnetic disturbances from the sun are caused by solar streams impacting the Earth. The features and concepts associated with IPY2, international polar observing networks, new instruments, radiosondes and ionosondes, rapid run magnetometers, simultaneous measurements at multiple stations, global current patterns for specific magnetic disturbances, called magnetic bays. And that means what came out of it was expanded synoptic data, higher spatial and temporal resolution, more evidence of global connectedness. Basically, synoptic studies are giving us more information about what things look like. Then come along the IGY, which Sidney Chapman was a major force behind. And he said the IGY's main aim is to learn more about the fluid envelope of our planet, the atmosphere and the oceans, overall Earth and overall heights and depths. These researchers demand widespread simultaneous observations. Notice that means that the emphasis is still on further synoptic studies. The emphasis is on exploration. But a lot came out of that. There was Antarctic stations, all-sky cameras, scientific satellites, and world data centers. And the major kind of discoveries that were made during that time was Akasafu's discovery of the auroral substorm. Whereas Silsby and Vestine had a static thing, the auroral substorm actually changes in time, comes and goes. And even more famous was the discovery of the Van Allen radiation belt. So space is filled up with radioactivity. The innovations and results associated with the IGY, interhemispheric networks of polar stations, new instrumentations, all-sky cameras, satellites, major discoveries, radiation belts, new concepts, the magnetosphere and substorms. So we had the exploration of space, 3D synoptic data, evidence of time-dependent global dynamics. And we come to the international magnetospheric study. The concept of that was that the complexity and the large spatial scale of phenomena under scrutiny demanded simultaneous measurements both in space and on the ground. That is, one needed more synoptic studies, which is not new, but the idea was that one of the reasons you need it is that they realized that the system is very complex, and that was new. The report that came out during the IMS was that many new questions have emerged, mainly concerning the cause and effect relationships among the dynamical processes, so we're coming to scientific understanding, and involving the magnetosphere as a single integral dynamical system. The magnetosphere is seen as an interconnected system. And we had the innovations from the IMS, magnetospheric change, IC1, IC3, Satellite Situation Center, coordinated data workshops. The famous discoveries was the flux transfer event by Russell and Elphick, and much more significant than that was the discovery that the magnetosphere and the ionosphere are linked through a permanent set of macro-scale field-aligned current systems. And the region 1 current systems linked the ionosphere and the magnetosphere and the solar wind. So now we had a mechanism, an actual physical connection between the ionosphere, the Earth, and the magnetosphere and the solar wind. Then we come to the solar terrestrial energy project. The justification concept was that framework for action states the main scientific goal is to advance the quantitative understanding of the coupling mechanisms that are responsible for the transfer of energy and mass from one region of the solar terrestrial system to another. And it continues, the program will involve coordinated observations with instruments on the ground, in the air, in space, theory and simulation studies, and data and information systems. Things are getting much more complex and integrated in these studies. So coordinated and integrated comprehensive 3D synoptics and modeling projects. What all of these programs did is that they organized and coordinated data gathering analysis. The IPY1 gave us synoptic observations, networks of polar stations. IPY2 added a third dimension. IGY gave us Antarctica and space. IQSY added the solar minimum, and IGY to IGY solar max. IMS gave us the satellite situation centers and coordinated data analysis workshops. And the Solar Terrestrial Energy Program gave us the numerical modeling. So IHY, which is where I'm ending, added the comparative heliospheric studies that Carl mentioned. These programs also provided thematic emphasis. IPY1 gave us mapped the phenomena. IPY2 explored the upper atmosphere. IGY explored space. IQSY complements IGY. IMS gives a study system complexity. STEP was study integrated interaction systems. And the IHY was to universalize heliospheric structures and processes. I'll come back to that, because I think that's really important. And of course, all of these systems allowed us to justify resource allocations under program themes, and this is where space weather started to become noticeable. So now coming to heliophysics as it sort of appeared in around 2007, it cannot be emphasized too strongly that the development of a solid understanding of magnetic activity occurring in so many forms and so many circumstances in the astrophysical universe can be achieved only by coordinated study of various forms of activity that are accessible to quantitative observations in the solar system. And notice this is in Parker's book, Cosmical Magnetic Fields. Somebody who isn't involved in heliophysics, but nevertheless is involved in system studies, that's Murray Gell-Mann, says, since we now know we're dealing with a complex system, he says, someone should be studying the whole system, however crudely, that has to be done, because no gluing together of partial studies of a complex nonlinear system can give a good idea of the behavior of the whole. That's a takeaway point for heliophysics. It's a complicated system, and you have to deal with it as a whole. Let's see, next one. So what I'm going to do is suggest a way in which one can conceptualize heliophysics. One can divide the universe into two large organized by two large-scale forces. One is gravity. Gravity organizes matter by pulling it together, and it creates planets, stars, galaxies, and that's the one that astronomy covers. And the other is magnetically organized matter. Magnetic fields push matter. They don't pull, they push. They create sunspots and magnetospheres. And the tension between the two, which occurs in the suns and on planets, gives us space weather, gives us sunspots, gives us solar activity, and gives us solar flares, and gives us magnetic substorms and magnetic storms. So if you think about it that way, that the universe is organized by two large organizing forces, gravity and magnetic fields, and they come together and have essentially have a tension between them, which gives us the things that are interesting to study, space weather. That might be one way to visualize what heliophysics is relative to what it is not. So this is one way one can organize the universe into an astro part, which is what one senses by remote sensing, and a solar part, that's the solar system, which one can sense by in situ observations. And one sees that they have the universe of galaxies and stars on the one hand, organized by gravity, solar system planets organized by gravity, and plasma astrophysics and solar connections and plasma heliophysics organized by heliophysics. The gravitational objects give us such things as the origin of life on planets, and the heliophysical objects give us space weather. So that's my idea, anyway, that you can divide the study of large-scale things into astronomy, which is gravitationally organized, and heliophysics, which is magnetically organized, and the tension between them produces all of the things that are interesting that change in time. So if you're thinking about a textbook on heliophysics from this perspective would have such chapters as spontaneous gravitation, generation of structures and transients, and under there would come such things as cellular structures, and that includes all magnetospheres and the heliospheres and things like that, and current sheets was like the heliospheric current sheets and all the rest. But that becomes a separate study, those things by themselves. And I'll just go on. Explosive energy conversion gives us all things like solar flares and magnetic substorms. Generation of penetrating radiation, this is important for space weather and satellites and astronauts. Magnetic coupling into the things like, this is where ionosphere and such things as that come in, dusty plasmas, and creation and annihilation of magnetic fields, with making sunspots and such things as that. Now that could make a book, which would essentially give us all of the physics which underlies heliophysics. One of the things I wanted to mention in connection with this idea that it's the comparative aspects of the parts of heliophysics that could lead to breakthroughs. And here's an example. If you look at the reconnection going on at the sun, looking at a trace image of a reconnection region, and the reconnection going on in the magnetosphere, just a sketch, these are the same scale. Now, the advantage of the two is that you can do in situ reconnection in observations of reconnection at Earth, and you can do remote sensing observations of reconnection on the sun. So putting these two things together would be a great way to view, within the context of heliophysical study, because these belong together in heliophysics, a great way to make an advance. So I will conclude with just this summary of what heliophysics program can do: organize and coordinate data gathering, analysis, comparative heliophysical studies, provide thematic emphasis, move from mission focus to general heliophysical concepts and processes, universalize heliophysical structures and processes, justify resource allocations for initiatives, for example, space weather and comparative studies, common data formats for comparative heliophysical studies, web-accessible data models. The CCMC is a great innovation there, and coordinated data analysis workshops for comparative studies. And I want to emphasize the idea of moving away from mission focus to heliophysical concepts and processes. And for example, the THEMIS was a good example of that, focusing on substorms, and MMS is a good example of that, focusing on reconnection at the boundary. So I'll conclude with just putting this picture back of what a heliophysics book might contain in terms of chapter headings. And I want to point out that we in heliophysics have different ideas of how that concept of heliophysics should become a definition, I suppose. For example, this new book of the summer school is titled Heliophysics, and that has to do with the idea that heliophysics has to do with active stars, their atmospheres, their impacts on planetary environments. So one can go in two different directions here. In that direction, which focuses on the actual physical objects that are making the phenomena, or on the physical processes that are different from other physical processes which divide the universe into two different kinds. And so with that, I'll thank you for your attention. Just wanted to point out, the panel discussion at the end of the day is an opportunity to go into these kinds of issues more in detail.
Thank you, George. And we'll bring Dick Fisher back. And you have which is your talk?
That's it.
This one?
It starts out with blackness. Probably use the presenter mode.
Yeah.
First, I would like to comment on how grateful I am for George and his insights, and for Carl. These two fellows undertook the idea of a revision of the way that we teach people, and they did it fearlessly, and I think they've had an enormous success, and I'm just dazzled by it. I'm going to talk about it not from the 25,000 foot level, or maybe the 1 AU level, but I'm going to talk about it as somebody who viewed this mainly in the trenches. When I was a boy, I was occasionally taken to either New York or Chicago and go to museums, and it was just heaven. I mean, there was all the neat stuff, truly. There were dinosaurs, there were mummies, and there was space. And I thought that was wonderful. And from about the age of 10, I thought it would be a really, really enormous thing if you had the privilege of being a scientist. So I was disposed towards that. When I was a little bit older and sort of in high school, the International Geophysical Year was organized. George has commented about this, and the only thing, the only thing I wanted to comment, I'm giving away all my good stuff here. The only thing I wanted to comment on was that there were a series of 6 posters that were created by the National Academy of Science to advertise the IGY. And 4 of them, we always laughed about it when I was in school later, that they were organized about what NSF thought was the nature of science, which was based on a Greek idea, earth, air, fire, and water. And those are the first 4 that you see on the left side of the screen. And as a kind of a, oh yes, at the beginning of the IGY, Sidney Chapman, Harry Vestine, Fred Singer, and others felt that the approach that was needed was to see a system and the Earth being embedded in that system. And so they added the sun and the Earth. And finally, there was brand new stuff, the first artificial satellite, and some of the earliest efforts on the use of artificial satellites for science on the part of the US and the Soviets. And this was given some recognition by a single human hand reaching up, grasping into the blackness, and there was no experience whatsoever. Nobody knew what space meant exactly at that time. Now I want to talk about an experience that I had that was pivotal for me, and that was this event. This is, I'm going to begin this with a space weather briefing, which is what Tom Bogdan would have done if he were doing this. This is the 19th solar cycle. And this is the sunspot number, a non-physical measure of solar activity. And right at the declining phase of it in 1960 in the fall, there was a large event, a large flare. And 2 days before the flare, I had been trying to remove an incomplete from my record at the little college I was going to by finishing a previous year's unfinished seminar and just take a single picture of something with a telescope and do something with it. So in a break in the clouds, I managed to take a picture, and lo and behold, there was a great big sunspot on it. Now, what I didn't know came about 2 days later, which was there was an enormous flare on the sun. And at the same time, an event now known as ground level event 10 occurred, and that means ground level event 10 was the 10th one that had ever been counted where the cosmic rays measured at the Earth's surface were known to have been generated on the sun. It was a very controversial result in 1941 when it was first detected, but this is the neutron monitor. The neutron monitors were a network that were scattered out by the IGY and were built by a brilliant physicist at the University of Chicago, Simpson. And they're still used, and you can see in the midst of an enigmatic thing, there's a great big drop in the cosmic ray flux, and this is known as the Four-Bush decrease, explained at the time as either a scattering or as a current particle interaction from the flow out from the sun. Well, I had access to none of this. I knew nothing about this until I was about, I was in the 70s, and I was working here in Boulder and had access to the library at NCAR and at the World Data Center. And I wondered what in the heck had I seen, actually. And what I knew about it was very, very simple. What happened was there was a tremendous geomagnetic storm associated with that event. And in Iowa, where I was going to school, we had aurorae for 3 nights that reached down past the Texas border. And this is one of the biggest auroral events of the 20th century. I woke up on the morning of the 16th after looking at this, and I had debriefed myself the night before, and the third night of a huge aurora, curtains brighter than Delta Orionis, but Alpha Orionis and Alpha CM were visible through the structure. Well, what I was doing there was, at that time, people in Iowa thought that astronomers talked like that. So I was trying to talk like an astronomer. And Delta Orionis is the brightest star in the belt of Orion. And the aurora were brighter than that. It was just my pathetic attempt to try and measure something. And I guess I looked at it in the evening from 9 to 11. In Iowa, that was a talk we used for daylight and not daylight, with AM and PM. But I left with a very strange feeling. I was extremely agitated and I was extremely restless. And I had only one feeling: I have to know more about this. Well, an interesting thing about it was that in a college that had 1,200 students, we had a library that had no books in it that I could find very much about this event. It was a strange thing. What we did have in the library was one of the posters, which is this one. And the artist, Herbert Danska, was a well-known illustrator at the time, and he attempted to make the IGY posters sort of homogeneous thematically in the following sense. They always had a circular or spherical apparition up here. They always had a Greek mythological person who was down here doing something. And then they always had icons that showed scientists working. I thought this was pretty interesting. Came to my attention in that I said to my professor, a guy named Bill Sandman, how do I learn more about this? And he said, I'll check with my advisor, who's a real astrophysicist, and he'll tell me. And he did, and we got a letter back. And his professor had been Eugene Parker, and he'd had him at the University of Utah. And Parker said, look real hard at the University of Colorado, where they've got this new department called Astrogeophysics. What a name, holy smokes. So I looked at this poster, and there are little icons here that show IGY assets that were distributed around Boulder. And in later life, I wondered if in some way Walt Roberts had the foresight to kind of use this poster as a recruiting poster for the AG department. Who knows? It was a possibility in my mind at any rate. The other things that are shown on here is a guy that had some misfortune in life. This is thought to be Prometheus, who was from a tribe of gods named Titans. They had a big war with the Olympians. In the end, he joined up with the Olympians, and he swiped fire, which belonged to Jove, to the creator of everything. And he gave it to mankind so we didn't have to sit in the dark and wonder how to read at night. And we could also eat cooked food. And so he was punished suitably for that. Now, I always wondered if maybe he was practicing a punk technique for a layup. But this is, in fact, a cartoon of the Earth being held in the palm of his hand while he gets fire. And this circle is actual, very, very close to a drawing that was published in 1633 by a guy named Christoph Scheiner, who followed Galileo. And what it is a superposition of a drawing made at noon, and you can see the rotation of sunspots as an illustration that the spots were actually part of the sun as opposed to something in between the Earth and the sun. Well, this poster had enormous influence on my life, and I recently discovered it, and it was pretty interesting. I went to school at the AG department. By the time I was done, I had learned an enormous amount of stuff in terms of breadth, because the curriculum, as Dr. Billings said to me, it goes from the deepest layers of the Earth out to the boundary of the universe. And I thought, boy, that's going to be a tough one to take comps on. And I was kind of interested to hear that point of view again today. But it was a very cohesive time. There were a number of people who had been recruited by Walt, and it made a department that was very cohesive. And I'd like to bring that to your consciousness, that what we're doing here is we're having a forum where your compatriots, the people you will practice the rest of your professional lives with, you have some knowledge of, you have some common background, and cohesion is extremely important. Well, I graduated and went on to the University of Hawaii. I didn't know enough to really do much. I'd majored here at the AG department in mountaineering and coronagraphs. So I did site surveys for all the big telescopes in Hawaii. And this is the first coronagraph that I ever built with my own two hands. And this is the first observation I ever took. And I learned an important lesson from this, which I'll give to you for nothing. This is an EPL that occurred in March of 1969. Little did I know, but way south of us in Kougora, Australia, there was a 10-kilometer diameter synthetic aperture radio telescope that actually imaged the debris of this event. And it turned out that what they saw was, after sunset, where I was a huge mass of material that was moving off the sun. And I always wondered if they'd gotten the time wrong on their platen or something like that. But at any rate, the lesson I was going to tell you is the public, NASA PR, media press, love the ST stories. Now, what do I mean by that? Well, we'll use use it as an adjective. Biggest, fastest, most dangerous, all of those things will attract the print press. And so I'll give that to you for nothing. I went on for another 30 or 40 years as an astrogeophysicist, sort of, and had a research career. I'll just take little chips out of it and you can look at the pictures. But the point I'm going to make is I could never bear an introduction or a comment or a biography that said I had studied astrogeophysics, because it always made the audience snicker. What is that, for goodness sakes? So I was a little sensitive about that. And in 2000, I took a job at headquarters as a government official, as an administrator of a program for the Science Mission Directorate. And it had a funny thing, which I'll just confide to you if you just don't do anything other than commit it to the right-only memory. I had a possibility of not only making policy, but implementing it. Now, that doesn't go over real well in a democracy. But I could play at both ends of the table. And so my predecessor was a guy that I'd been in Skylab with, named George Withrow. We came up with something called a strategic declaration. In this election year, you're going to be very familiar with this. A strategic declaration, you say something first that's incontrovertibly true. Nobody can argue with it. And then you go on to say what you think you should do about it, what you might possibly do about it, what would be a good thing to do about it, and why there would be benefits. So the strategic declaration we came up with for the Sun-Earth connection was, at the center of our solar system, there's a magnetic variable star that drives the Earth and all the planets in its sculpture space itself. And that research on this has given us results that have cultural and cultural and intellectual benefit, but there also are political and economic reasons for going into this. And that was sufficient enough to get some support. Now, I want to talk about science because George did, I thought, a wonderful thing by talking about the history. If I could do nothing else, I would commend to the students today to go to the internet as soon as you get out of here or whenever it's convenient. You can do it while you're sitting there, I guess. And go to the TED Talks. And in the TED Talks, there's one by a guy named E.O. Wilson, who is a scientist and is a professor at Harvard. And he came up with replayed a concept which was developed about the time of Darwin, consilience. And it's how do you make new science? And consilience is the linking together of principles from different disciplines, especially when becoming a comprehensive theory. And George and I remained excited about it, have been interested in heliophysics as a consilience. Now, there was very little codification about this until one day. Well, first of all, I'd say that people such as we had enormous support in those days from the scientific community, and I cannot say enough about that. That people were cooperative and worked hard for the greater good. And George took on an interesting thing where he considered the possibility of do we have the wrong name? And he said, no, I don't really want to get into that. But later at a conference, at a Chapman conference, he said the following things, which you can read for yourself up there. And George was very, very supportive, and I will be forever grateful to you, George. Thank you so much, and Carl, for your remarks and thoughts. I won't read this. You can read it yourself, but you also heard it. Now, this came into codification when about a year later I got a call from the administrator. Now, I didn't get that many calls from the administrator, and it did kind of give me a chilly little moment. And he said, Dick, we're in here in my office. We're doing the budget for next year, and I want a name for your department that is different than the Sun-Earth Connections Division, which is hard to say and makes Congress people laugh. And I thought about astrogeophysics for a second. And he said, so give me a name today that we're going to use as we construct this budget. And I got to have it, so call me back in 10 minutes if you need to take that long. What's it going to be? And make sure that it ends with physics. Well, I mean, if you're holding two deuces, what are you going to do? Check to the next better? I guess so. And I was at a meeting of the advisory committee. And as I had the whole staff there, and I said, what do you think, guys? What are we going to do? And there was a gosh, well, I don't know, gee, so forth and so on. But there was a little consensus that heliophysics was going to be as good as we were going to get for the administrator that day, and that's the way it's been ever since. So that is a story which you can regard as a space story, or perhaps it's a fairy tale. Now the next image I'm going to show has been questioned, but it is not Lika's 21st birthday party. That's not true. Because that would make her, you know, a lady of a certain age now. She was actually only 18 when this picture was taken. And there are other questions that we don't really understand very well, like why is the guy in the gray suit standing so close to the food? But we really can't do it. This was the beginning of an agreement between not only the individuals, the scientists involved, but between agencies and institutions. That there is value in cohesion, there's value in education, there's value in seeing consilience in system science. And so it was kind of a great day. Tom, I cannot remember why Ernie was there. Do you have any? Can you?
He was representing space weather.
Okay, space weather. Okay, that's it. All right, I want a moment of reflection back on Danska's poster. Everything in this poster that you can see is kind of weird. First of all, the cartoon was drawn before the solar wind had actually been discovered by the Soviet lunar spacecraft. So the connection between the Earth and the Sun is based on a conjecture that had been made in the 30s that there is a current flowing from the Sun and interacting with the Earth. Second thing is that the callouts are only about phenomena. If you go to the original brochure, which is online, it just says aurora, airglow, geomagnetism, magnetic storms, solar flares. And so there's very little insight into this. It was the picture of the people and the facilities that really turned me on, and it was particularly the globe that was made out of blackboard material because they were trying to figure out, this is something where somebody was trying to figure out where was the corona when you couldn't see it because there was only coronagraph images, and that's a hard thing to do. There were also the other telescopes and whatnot, and in there are pictured two people that I knew pretty well, Dorothy Trotter and Sabina Schaffner, who were working at the High Altitude Observatory, or had worked at the High Altitude. All of this stuff, every bit of it, does not exist on the Earth. The people are all gone. So why are we talking about this today? Well, that's an interesting thing. We're talking about it because it generated at the time enormous cohesion across a broad area of science, and that has been maintained. There is a universal interest in what happened in the past, what's happening to me right now, what's going to happen in the future, and those are good intellectual bases for the investigation of things that you don't understand very well. So for me, this has been a wonderful opportunity to see the people. I think the most important people in the room, as we've identified, are the students and the staff here today. And you have my undying gratitude and admiration for the job that you've done, and including the National Center for Atmospheric Research and UCAR, which is a post-World War II impulse to try and move from an economy based on the utility of natural resources till they run out to a knowledge-based economy and in support of institutions. So that's all I have to say today. That's the story of how I went down the road towards being at the Heliophysics School today, and it's been a great privilege to talk to you. Thank you very much.
Not only the summer school, but the Heliophysics in general. And then when we come back, a little bit more about current events, and then a little bit about the future. So we'll be back here at 3:15.
You have to be kind of careful with this one. It's not really...
Oh, it's on.
Well, it's got a bad switch. That's right.
Okay. Yeah. You want to take your machine? Yeah. Oh, yeah. This is the. Oh, did you get it? Okay, great.
It's a military grade laser.
Yeah, is it?
It's the only one that I've got that's working today.
Oh, I see. Okay. Here, okay.
We will have to be on the spot with the mic because I
This continues, right?
yeah.
So that's
No, we should leave it.
You think we'll leave it?
Yeah, we should just leave it standing.
You're not using the one on the left, are you?
What on the left? Yeah,
You're
but
not using this, right?
no,
I'm just gonna
you
leave
can
this
leave
here.
that there.
So can I say 2 words?
Yeah.
Okay. So if you're not very, very, very careful, you're going to end up like Neil and Andreas. So Neil Savani, many of you already know. Andreas Munez. Oh, nuts. Jaramillo. My 11th grade Spanish teacher would be very upset with me. Have been deeply involved in as participants in heliophysics education. Since Andreas, you did an RAU at Bozeman, right? So as in the solar physics group, and got in love with heliophysics there, and then eventually came around to coming to the summer school. Neil, I first met in something like 2006, 2007. You were in Boston at the SISM Summer School and then came to the Heliophysics Summer School, and both of them have been now lecturers at the Heliophysics Summer. Oh, and of course, both of them have been Jack Eddy Fellows. So there's a lot of history involvement in the not just in the planning of the summer school, but also as now we have, after 10 years, students coming back and participating as both lecturers and then in this celebration of the summer school. So I am going to hand it over to them for a very intriguing title of Demographics of the LWS Heliophysics Summer School in Haiku form.
Okay, so this talk has two parts actually. As you probably, as the students and the lecturers, have received my emails asking you to fill a survey and send a haiku if you want. So this is what we're going to. The first thing is that I'm going to show you some of the results of that survey. And some of the haikus that I liked among the ones that I received, not all of them. By the way, I want to kind of make a booklet of haikus about heliophysics. So if you want to make a haiku and send it to me, I think I'm going to wait, make an announcement, ask for more haikus from outside the school, and then compile a little booklet to be the 6th Living with a Star heliophysics book. So for those that don't know, the haiku is a short poem that originated in Japan. Sorry, and before I continue, the second part will be with Neil. So the first part is kind of like a little bit about the data behind us. The other one is going to be a much more personal part of the presentation, where both of us are going to share a little bit of our experience as we have gone through all the different steps. So haiku is a Japanese form of poetry where you have the only restriction that you have is in the amount of syllables that the poem is composed of 3 phrases with 5 syllables, 7 syllables, and 5 syllables. And traditionally, it's about the nature and the seasons. But in the English language, it has been, especially I guess in the US, has been widely adopted. And it's quite fascinating because I have actually quite fallen in love with it now that, because the English language, since it's not phonetic, is really crazy. You don't, sometimes you see like this super long line and it's just 5 syllables. Sometimes you see a short and it's the 7 syllables. And so it's kind of, it has some form of magic. And so that's basically what I'm going to be showing you. So the very first haiku actually that I want to show you is paying homage to someone that I admire very much that has been instrumental in bringing this forward. And so it's this: courage, compassion, creativity, passion, inspiration, Lika. And my pen name for this presentation is the Survey Monkey. So first starts a disclaimer. Surveys gone unanswered, making results uncertain, introducing bias. So I tried to reach out about 350 people. I got about 130 answers. So I don't know. I mean, hopefully this, and there are some things here and there that make me think this is not completely representative, but it paints an interesting picture. And I'm going to show you, as I say, not directly related to what I'm talking about, some of the haikus that people have sent me. Young minds receiving seeds of the local cosmos, horizons expand. So, where do we come from? More than 28 countries, all over the world. And so here is a little map that I made in Google Maps of the students that answered my call. And so you can see that basically you get from all continents. Like Oceania is missing, but this here is one of the things that. No, I have that data. I'm not going to show it, but this is where they actually originally from. Yeah, I also have kind of like the data of where they when they did the Living with a Star summer school. Where are they now? And I have maps here. I will share this map with all of you online. These maps that I made. Here is for the lecturers. So, and this is one of the things that is quite interesting of this exercise, is that it shows how really it has become a more inclusive exercise, right? And you will see it very clearly when I show you the demographics, right? When you compare kind of like the older generation with the newer generation, it's quite interesting to see how this distribution changes. New friends and mentors in a mountainous retreat, science, sun, and space. Race, ethnicity, quite difficult to measure, many approximations. And this is something that was very difficult because I basically had to play around with, I mean, the concept of ethnicity and race is very important in the United States, and it's becoming more important over the world in general. But there are many countries where the countries are so homogeneous that this basically where we are from is our ethnicity, and that's what defines us. And so it was a difficult question to ask because I tried to basically, if people were in the United States, I asked specific questions about ethnicity. But if people were from outside of the United States, I basically kind of tried to make a map between origin and race. So kind of like this is folding together both things. But still, it's interesting what you see. So here is all lecturers that I got answers from in terms of ethnicity. So I have, you will see the categories. In this moment, I don't have all the categories. Not everyone, all the categories that I chose are represented in the lecturers. So you have people from East Asia and South Asia. East Asia is kind of like close to the Pacific. South Asia is mainly the subcontinent, so like the greater India with Pakistan. Hispanic is anyone from Hispanic origin. So it can be a Latin American or a person from Spain. And then white is white Americans or Europeans. And I have also Middle Easterns, but they are not in the lecturers, okay? Now, when you look at the students, right, this is just the students. Now, this is one of the things that I think is beautiful and that I think it's really incredible about this school being an international thing, right? You have people all over the world, very well represented. So you have, here all the categories are present. And of course, you still have something that is kind of like a cross between the demographics of the world and the demographics of the United States. I mean, most of the students are still American students. But this is the other thing that is quite interesting, because when you look only at the United States, so here, since I ask people, where are you from? They say I'm Americans. I make the same kind of analysis, but only with people from the United States. And so most of the lecturers are from the United States. And you have essentially, all of them are essentially white, and there is like a couple of East Asians. But when you look at the students, so the students, the people that come from the United States as students, then you actually have something that looks much more like what the United States looks like. And so this is one thing that I find very encouraging and positive about this whole exercise, and is that really to make science something that includes everyone, right? And that's also something that I think is very positive of having, I'm as a foreign student myself, right? I am deeply grateful of the opportunity of attending something like this. And then actually when you look at the United States, and we're still having ethnicities that are races that are underrepresented. But when you bring people from all over the world, then it becomes like the rainbow, right? So that was one of the nice things of this exercise. People from all over the world, very well represented. This was probably the most clever haiku that I received. LWS, MHD for CMEs, PhDs to be. Male-female ratio, still some room for improvement, getting almost there. And this is the other thing that is interesting. When you look at the lecturers, I mean, we don't necessarily, we are 50-50, essentially, more or less, give or take, right? Maybe because of interest and things, achieving a perfect split, even split is not necessarily perhaps, but there is a clear discrepancy between the demographics of the world in the lecturers and the demographics of the world in the students. And now when you have 40% female students, 60% male students, you're really getting close to that point where you're in the uncertainty, right? And I think that that's another thing that is very positive, because ultimately this is what it, ending privilege is a question of opening spaces. And so when people have access to the spaces and the people that have the privilege give access to everyone to those spaces, then everyone works together to dismantle privilege. Connecting the sun, dynamo to corona, surface flux transport. Student permanence. Can they stay or must they go? A hard bottleneck. So this is the other thing that I wanted to look is whether we can stay doing what we want to do. And we're going to touch a little bit more on a personal level with Neil about this later. So the first question that I said is, well, I clean my data for people that have not graduated yet. So these are what the answers that you're looking at here are people that had defended their PhDs in 2015 and before. Now, of course, this is one of the cases where you can see there is a very likelihood of a bias here, and it's the sense that perhaps the people that have left us are among those 200 surveys that never got an answer, right? But the people that I could still reach, most say are still in science. Now, the interesting thing is that now from here, we can take one step forward to a place where we can actually trust the results better, which is whether you're still doing heliophysics, right? Because we know that out of these people that said, yes, I'm doing science, then we have most of us are still doing heliophysics, which is pretty nice. I mean, this, in a sense, that's what we're trying to strive for, right? That this new generation our talent stays. And then the other question that I was wondering, and this for fun, I did this, but because I could do it with the data, is have people changed their topics? Are you still working on something that was what you were related directly to what you were working on your PhD? Or have you changed topics? And about 40% of the people have moved on to a different topic, perhaps related, but not exactly the same. I have to say I'm not one of those. I have stayed within the topic of my PhD, but I have broadened it. And this is kind of like a fun thing that I did. Great Indian students. When one of them goes back home, another arrives. Because I ask people, where were they when they were doing the summer school? Where were they born and where they are now? I was wondering if there have been some net flux of people in or out of the United States. And basically what I found is that out of the answers that I got, 2 Indian students went back to India because I could see that they went there. But 2 Indian students came and are now in the United States. And so essentially people kind of like, there was there is a net flux of people into and out of the United States. And in our particular population, they happen to be all Indians. The sun is a star, like trillions in Milky Way, but dear to Earthlings. Teaching heliophysics, the summer school is useful. Lots of material. This is something that kind of touches a little bit on the topic of the presentations that will come after, but I was curious. This was an opportunity that I wanted to take to ask people that have used this to teach, what has been the most valuable contribution to their lectures of all that they were exposed here in the summer school. So this is actually the lecturers, because a lot of the lecturers also have like teaching positions. And most of my data in this regard were the lecturers. It's interesting also to see a little bit about the difference between the 2 populations. I didn't have many of the educators that were students answer, but still, the internet is the most valuable thing for everyone. It's highly valuable. This is like a question where you grade different things as valuable or not valuable. Everything can be absolutely valuable for you. So you don't need to rank. So each one of these areas tells you how the people answer to that particular material. So I ask whether attending the school itself, whether the books that you took with you, using the CCMC website, just the World Wide Web, and interactions with others that you met during the school after school. So for us as lecturers, the people that also do research in heliophysics, perhaps the most valuable thing, I guess, was the internet, followed by attending the heliophysics school itself. But when you go into the students, so educators that come here to learn about heliophysics so that they can teach, without a question, being here was the most valuable thing. So I think that all this shows also the power that the summer school has, right? The fact that not all of us are researchers, but we also have educators among us. And for them, just being here and being exposed to all of us and to the research and to the lectures and to the lecturers is the single most valuable thing. And so this first part of this very short talk is going to be what I thought was my favorite haiku of all of the ones that I got, which is sun, flare, solar wind, earth, ionosphere coupling, living with a star. Okay, so that's the first part. And now comes the second part. And as Nick said, both Neil and I have been part of this whole story in many roles. And Lika asked us to share a little bit our experience. And we decided that this was going to be actually a part of our lecture that is actually more targeted to the students than to anyone else. Because it feels a little narcissistic to just do a presentation about yourself. But what we really are trying to strive for here is that we are you, right? We are you 5 years into the future. And we're closely enough to you that our stories are essentially the same stories. And so that's kind of like what we're going to do. So it all starts with very humble beginnings, right? And it's essentially how we got into science, right? And in particular for me, it was a question of being exposed to cosmos, to Carl Sagan's work, and just seeing him get into that spacecraft and just go to the other stars and everything. That's really where all this started for me.
So for me, it was slightly different. I'm a British-born kid, and I actually spent much of my time not necessarily starting with astronomy, but actually with my hands in the mud and looking at the natural world. And I actually got very excited by things and shows by Sir David Attenborough rather than Carl Sagan. But it was only sort of later on, as I got into my teenage years, that I realized, looking up in the stars had just as much wonders as looking down into the mud.
Then our first steps in heliophysics. So as Nick said, I came here in 2003 as an undergraduate student. That was my first time out of my country. I'm from Colombia, by the way. First time on my own, without my parents. And that picture is a picture that I took there as part of the RU program. When I came to Montana State University, actually, my internship was funded by the Living with a Star program. And I basically fell in love with everything that I was doing, the people that I was doing it with. So that's why I decided without hesitation to come to Montana State to do my PhD in solar physics.
Again, for me, it was a little bit more complicated. So in fact, when I was deciding at undergraduate level of what I should pursue, I found it a little difficult. I was torn between the real-world applications of which I felt was applicable in chemistry for me, and that of my love of mathematics. And in the end, it was the mathematics that won out, and I stuck with physics and spent many years and 4 years doing physics. And spent in total 8 years in London, which I thoroughly enjoyed. And so that's how I started getting into it.
Okay, so then we come to our PhD, right? Which is when you become an expert on a very small part of the rest of the universe, right? And in particular, my focus was making better models of the solar cycle. So how do we get everything that we see, all the signatures, magnetic signatures that the solar cycle has, how can we get them out of a model? How the magnetic field gets changed, its polarity is reversed, how you end up having 10 years, 11 years cycle, all these things. But my focus, specific focus, was just this simple simulations.
And for me, my love of space sciences really started from the courses I chose at undergraduate. I had a great deal of ability to choose a varied number of topics, and it was always the space sciences that greatly excited me. And it's to that end where I really realistically realized that a career in what is essentially a hobby was possible. And so for me, I chose that, and I looked into what I could do, and I chose a topic which was CMEs, and I looked into what was available, and I started looking into my career at the dawn of the stereo mission. And I felt that was the new instrumentation that was being launched had some great advantages, and it was what I effectively thought was great disruption into the industry or the community, and it was that which was going to give us a great understanding of the phenomena and potentially have bigger and broader impacts for the relevance of space weather.
So far you have these parallel stories, right, which can be any of you, but then now they start getting, we're doing in topics that were at first sight completely unrelated, right, coming from different parts of the world to different parts of the world. But then here's where basically one of the things that we want to show you that ultimately we all have a similar kind of narrative, and then part of the narrative is the summer school. So I was here in 2011 when I came as a summer school, and it was for me a time of enlightening, right? I have been focused on this little model of the solar cycle without really grasping all the possibilities that were there in the world.
That was essentially the takeaway point I had as well. When I investigated my research topic during my PhD, it's very focused, and I didn't really go into the details of the science of that one figure, but you can take it on me that it was very focused. But what I remembered vividly was always wanting to know and understand the broader context of what I was doing and its relevance to the real world and its applications for that. And it's for that reason, which is why I found this summer school to be perfect in essence. It provided and catered to students towards the end of their PhD and gave them the broader context that was needed to understand why they're doing what they're doing.
So now I'm going to mention a bit how has the research that I did in my PhD then grows, and we're going to both of that do that, but now it's just, I guess, a slide per person. How it grows into expand into the heliophysics domain, right? So in particular, what happened is, in my case, was that I started to realize how important the active regions are in the heliospheric system as a whole. In particular, for the active regions, these bipolar structures, I mean these bipolar structures that you see in the surface of the sun, and their numbers change with the solar cycle. But they're really critical for determining, for driving this evolution of the large-scale magnetic field, but they also defined the properties of the solar corona, and thus the solar wind, the cosmic rays, solar irradiance, and it's all these connections where finally you transcend from your small subdomain into something that becomes more integrative. And in particular, for my Jack Eddy Fellowship, what I wanted to do is create a catalog of active regions that it doesn't still exist in the world. Actually, it has been much harder than I thought it would be. I have been working for the last 4 years on this, but I have made great progress. Going to all the instruments, fixing their data that were just gathering dust, working with students to make sure that the properties of those active regions are measured properly. And now we have achieved a milestone where we already have now the 4 cycles, and we're entering a phase where we're going to be able to fix this, to make sure that everything is as it should be so that we can start using them. And especially now my personal interest goes into forecasting. These are the building blocks of the solar cycle and heliospheric variability, and then we can do that to make better and more accurate forecasts.
Yeah, so for me, starting as a postdoc, I was awarded the Jack Eddy Fellowship, and I felt that had a great advantage to my career development. It really showed me that world-leading scientists had confidence in my potential to make impact, and in fact, more than that, just suggestions and ideas for new research. And the fellowship allowed me to grow independently and work on several different research domains through the Solar Division at the Naval Research Lab and the Heliospheric and the Space Weather Labs at Goddard. And through that time, I was able to work on a varied amount of projects, which ultimately culminated after 6 years, I guess, into what is in essence the 4 figures that you're seeing up top. And this is an attempt of creating a forecast for the magnetic structures of CMEs. And what you're seeing here is a summary of all the different data sets, or some of the varied amounts of data sets, in being able to create this and focusing on the different topics. So from down to the sun, to the in situ data at L1, and then going all the way down to the Earth and looking at the KP index. And so what we've got actually here is actually something that we're now testing with the summer students at Goddard in an operational setting. And so that adds to the real world effects, which is what I've always been driving towards.
And so then we are able, given the chance to give back, right? Which is now that we have kind of like made that connection and gradually also start gathering knowledge that we can now share. We both have been invited to teach here in the summer school, and it has been an incredible experience, because when you teach, you strengthen your understanding of the world. And so you come here, we teach about our subjects, but we again come as students because we have again exposure to the lectures of all the other lecturers. And so that's one of the things for me that was the most valuable thing of being a lecturer, was being able to share with the students and interact with the students and share what I have learned, but also again, always again, be a student again, and then use that to keep growing.
Again, I think it's very similar. Coming back this week to do the lectures on CMEs it's been an emotional one. It's been a long road, and you see your career track over the last 6 years, indeed, for me. And I see the excitement in the students' eyes and their passion and energy towards the subject. And I think that is something that we should always keep remembering.
So the last thing that we wanted to share with you is basically how all this that we have been trying to tell you comes together. And it is basically, it's kind of like a life lesson that we have learned now that we're entering a different stage of our careers, which you will be entering very soon, which is hitting the wall and making it to the other side. The path that you have followed, most of you have followed until now, it is somewhat like an automatic continuation, natural progression. You go from your undergrad and master's, you go to your PhD, but you never have to worry really about funding or where you're going to be next year. And perhaps one of the things that we wanted to share with you is most of you are going to enter this period, which is difficult. is significantly more difficult than anything that you have done today. And so one of the things, we wanted to basically tie everything that we have told you together to these two particular topics. One is that the challenge of going from your first postdoc into a career scientist increases significantly. And that, for me, it was very hard because I was not prepared for that. There was a significant mismatch in expectations. So knowing that this is a reality, we think is very important, and we just wanted to take this opportunity to just mention it to you.
But we address and we recognize the challenge, but there is a solution, and you can get to the other side, and that needs to be highlighted. And we do believe our solution to it is being to broaden our scientific impact, and by connecting the expertise with the rest of heliophysics.
So when you face these difficulties, know that you're not alone, and you have not been the first, nor will be the last, and that there is sunshine on the other side. So keep calm and science on. Okay, thank you very much. And if you want to talk with us about these, if you have questions now or if you have questions later, feel free to reach out to us. We're happy to talk with you. Ricky.
Yeah, I like your pie chart. Very optimistic about how people who attended school managed to stay working in heliophysics. And your last point is one that's very important, I think, for a lot of students. Do you have any more details on how they made it across the wall?
Well, I guess we probably should answer this question. You both, I mean, we probably will have different things to say. For me, I guess the important thing has been broadening this, like, as we said, because when you broaden your scope, you can reach more people. And so you're able to communicate. This is what I think is critical about the summer school, right? That the networking is absolutely critical for this, for taking this, going through the wall. So this is a networking exercise. You're meeting here potential mentors. You're meeting here your peers in the future, with the people that you're going to be writing proposals with as researchers. And so networking is absolutely critical, and making sure that your message cuts across. You can always give a spin to what you're doing so that it fits within this bigger picture. And that is going to help you when you ask for funds. That's going to help you when you look for jobs. That's going to help you become a better communicator so that people know, this guy, yeah, I like to see these talks or whatever. And so that starts, all that kind of builds up so that finally you make it through. And then you build the experience. The hardest thing is that you have not been, partly because often students cannot be their own PIs. You have never written a proposal. You have never submitted a proposal. And then one of the biggest hard of crossing the wall is that when you write your first proposals, you're competing with heavyweights, people that have been writing them for years. And so all this networking, all the putting what you're doing in a bigger context is very critical for making it through the other side.
So for me, actually, I wrote this down because I wanted to be very clear to the students, actually. And my advice was strive to do the best science you can, develop the best ideas you can, collaborate with as many teams as possible in different areas. And most of all, remember to keep an eye on the bigger picture for heliophysics. And the rest will hopefully fall into place.
I think I gave Nick the hard task of actually introducing everyone, and now that it is his turn and Jan's, that I have to introduce definitely Nick, but also Jan. So Nick kind of feels that sweet spot between deans and students. Deans are a little unapproachable in some sense because there is a big generational gap, and Nick kind of fits that gap. He's the one who brings the students together to interact with each other, to interact with all the lecturers, to interact with the deans. Nick is from BU with a PhD in physics, but most importantly, I think he's someone who deeply appreciates education and has played a very important role in kind of supporting the lab work that the students have been doing for many years now. And Jan, who is, of course, has been a dean, in fact, he is one of our longest deans, also has been very interested on the educational side. What is the educational impact? And you got some feedback from the students, and they are going to share more with you. And I think along with teaching classes, this lab work, which incorporates modeling from Community Coordinated Modeling Center, that hands-on experience, I think has become a very vital part of the Heliophysics Summer School. So Nick and Jan are going to kind of give you, description of what has been accomplished here.
Hello, I'm from Scotland, so I'm kind of that little spot someone didn't put on. But of course, the reason they didn't put it on the map was because I didn't fill out the questionnaire. I might guiltily go home and fix it for you, so I apologize. But what I want to say is that this is going to be an experiment. One of the things that Nick brings to us is social media in different forms. How many of you wrote home to your parents or others a postcard this last week? How many of you emailed or Skyped or a family friend or otherwise? Yeah, okay, so that's the difference between us. I use this regularly. I was in Europe last week, 2 weeks ago, and sent 6 postcards home. Didn't use Skype or anything. So this word fossil, a few of us are fossils in that sense. But as you've probably gathered this week, Nick is in there among you using social media and other things. And when we talk about heliophysics as being a kind of a system-level problem, and us old fogies only know a little bit about our little niche area, the big problem is communication. How do we communicate? And we heard from several speakers that early on, as we tried to break these links, we found that there's different vocabularies and everything. So today I was watching a few of you working with the ionosphere, and I'm pretty sure you had never come across these terms before that you were looking at to do with something as simple as a pressure level in an atmosphere, composition. It's nothing common vocabulary-wise, even with simple vocabulary. So to cut a long story short, watching these heliophysics summer schools over the years, the big winner is the communication between you. And I'm hoping as you leave here, you maintain these links with each other, especially as your careers blossom, and they will, whether it still is in heliophysics directly or an associate science field. What Nick is going to do to you today is actually force you guys to do some work. You're thinking, I'm going to stand up here and Nick's going to follow and tell you about the history of education and educational products. We're not going to do that. Nick's convinced me and Lika that it'd be okay for you guys to have an opportunity to think outside the, well, whatever you want to call it. But the idea is we're hoping that you are our next generation. 10 years from now, what will things be like? So that's the kind of hint. Nick, are you ready to take over and just get the ball rolling?
So, oops, let's see. So I'm imagining a time when 10 years from now, it's 2026, Amitava's group has solved fusion, and he is touring the world to great accolade. Ida is playing hockey in Minnesota. Lika is leading the International Aeronautics Space Administration and has tasked Andreas and Neil to run the summer school. Right? And so it's 10 years from now, and you guys get a phone call. And it's from either Andreas or Neil, and they say, we need you to lecture on a topic for the summer school. Okay, what are you working on, or what do you want to lecture on, right? So I want you to get back in your groups one last time. And I want you to come up, I don't know how much time we have, but let's take about 15 minutes. And I want you to come up with topics to lecture on. And I'm going to give you some categories. The first category that you to work on is a retrospective lecture of research that hasn't happened yet. So it's a mission or a research topic or something that's developed in the next 10 years. So by 2026, you say it's time to do a retrospective of that and recall it. The other category is a topic that is a current research, current tool, current mission that is being done or planned in 2026. Okay? And the third category is a topic that involves an aspect of science fiction. Okay? Somehow incorporate some sort of science fiction type idea into this research topic that you're going to lecture on for Neil and Andreas. I have sent you all a link to a Google document so that as you come up, what I'm looking for is, as a group, you should come up with these topics. And I'm looking for one sentence, either a title or a sentence description of the topic that you're gonna come up with. You don't have to like fill in all the details, but just I want you to imagine this. I want you to project yourself forward. And so Lisa Upton is back joining us again. Are there any other former students from the summer school? Oh, yes. I'm going to invite the two of you to join Neil and Andreas, because the hard work that the deans have to do is they have to come up with some organizing theme for this. And I'm going to invite them to also participate in this. And I should send you the link also. And you're going to so once we hear from the students, you guys are going to like come up with guys are going to tell us what the organizing theme is after we've heard from the students about what their topics are. All right. So this is just like the lab, right? I like stand up here, I tell you what you're going to do, and then you guys are going to go to work. All right, so move around, get your groups again, and have at it. I would encourage the more senior of you who to listen in, but I would ask that you don't kibitz too much. Carl's looking at me funny. Do you know what kibitzing is? It's when you stand over a chess match and you go, "Oh no, you shouldn't do that." Oh. Right. Oh no, that's the wrong move, right? And you're very annoyed. Yiddish term. So we got about 15 minutes on this. So we have to start going through some of these. I've been highlighting some of I've been highlighting some just to call them out. But maybe group one. What's your favorite? What's your favorite of the three that you, or the several that you put down? Huh? What? The first one? Huh? Okay, you got to speak up. I can't hear you. Does it have a good acronym? Does it have a good acronym? Must. Okay. Okay, great. All right. So group two is Solar Probe plus plus plus. Right, deep into the photosphere and the coronosphere. Okay, great. And I like the quantum, the whole quant. All right, maybe this one's my favorite. Because it's a year before. Okay, great. Space weather impacts at Jupiter's moons. Oh, direct solar imaging with Google Glass. All right, very good. I like it. I like it. Burn, baby, burn. How do we solve the coronal heating problem? Wait, somebody solved the coronal heating problem later on, I think. Solar C. Okay, finally funded. The effects of space folding on the heliosphere. Vacations, a look at solar cycle improvements of space weather predictions, Orion spacecraft, and astronaut safety. Okay. Oh, what? Sorry, I missed it. What do we need to know about interplanetary travel? Mars vacations. All right, very good. I like it. I like it. Oh, be quiet, you. Telescope. So using solar gravitational lensing as a for a 1 meter resolution of exoplanets. Excellent. All right. Jenny is swimming with the space whales. Here, I'm going to put this all on one page so we read it. The underlying story of plasma turbulence was caused by these space whales. Very good. All right. Physics of the interstellar medium with Voyagers 1 and 2. So we're now beyond the heliosphere, and we're still getting like little. So we've had to have built a super space deep antenna, super deep space antenna group to see this. Oh, nice! I love it. Gotta love it. And alien species that came to Earth protect themselves from solar radiation. Okay. And let's see, we've got stereoscopic missions. Oh, I like this. Interplanetary, a new field of planetary lab plasmas. So planetary-sized lab plasmas in a lab, or planetary-sized plasmas in a lab to study the ring currents. Very good, okay. Literally lecture on the mission, delve literally into the sun, I get it, all right. And altering the sun, nice. Very good. So what are should we go to our there's still more, yeah. Tools. What do you like here? Who's group 8? You're great. Oh, group 8, great. Okay. So if you live in Iowa, you're good. But in certain parts of Michigan, you're fried. Okay. All right, very good. So group 9 is our deans over here. So what are some of the organizing principles here? You guys want to? So they placed Pokemons on Mars and on the moon. Okay, all right, very good. All right. So what? Oh, right now you're still developing your own lecture topics. So, do you see any organizing principles in this?
It seems to be a lot about space weather on other planets throughout the heliosphere.
There seems to be also like a lot of, I mean, it's almost like when we're in space fails pointer, now we have such a good command of geophysics that basically now there's a lot of thing about tourism I saw and
Yeah. So it's space is now an industry. It's where we're exploiting space as a for its economics, and now we can, and now with the science is really even that much more important.
yeah, it's more like the heliosphere is now almost conquered. So the science now is outside of the solar system.
Uh-huh.
The biggest, and then
Eh.
inside the solar system now is like perfect forecast and issuing warning to tourists and
So like the weather right now is the space weather channel. You can get it on cable's probably the wrong, outmoded at this point in time, but you can get it on the ISS TV. Okay. It's is the beyond, going beyond the heliosphere. Okay, good. All right. Yeah. So I think I'm getting the high sign. Very good. I like it. I like it a lot. And now we have we've captured all of these ideas, and we can hold on to them till 2026, right? And see what's come out of it. Okay. So with yeah. All right. With that, I think we're going to turn it over to the panel. Is that right? So, you guys, I think, have a tough act to follow, because the panel is going to be moderated by Tom Bogdan. I'm like paying attention to what. Okay. All right. So I'm going to close this now because. Well, thank you again for all of your hard work making me look good. All right, so I'm going to turn this over to Tom Bogdan, who is going to introduce his panel to talk about what they think the future, the next 10 years holds for us. Yes, so this has been something they've been thinking about. They knew about this in advance. This wasn't sprung on them. They knew about this in advance, so they've been thinking about it for a little while. But, so...
Do we have any more microphones?
Oh, yes, please.
You should this microphone.
All right, welcome to the last session, which is going to be very forward-looking. We've asked these distinguished oh, sorry.
I was just going to give you an introduction, but for a person here, he does not probably need introduction. He is the biggest monarch of all, I guess, having been here at this institution for a long time. He was the director of Space Weather Prediction Center, and then he was the president at UCAR, and someone I have known for many decades. So, Tom, it's your panel.
Thank you. Thank you very much. So my name's Tom Bogdan, and we will get you done on time because we know there's a reception waiting for you out there. We have assembled a panel here of probably the 5 most distinguished heliophysicists who have ever worked in the area. No, that's absolutely true. And before they came here, we asked them 2 questions. Question number 1 is what you just did, which is, where do you think the breakthroughs are likely to be in the subject of heliophysics over the next 10 years? From your perspective, where are those breakthroughs? We asked them that question so that you would all be in a position to jump on those fields very quickly once you've left here and published much faster than they can in those areas. We're going to spend the first 30 minutes discussing their answers to those questions. Everyone will get 4 minutes, and then that'll leave a little bit of time for you to ask them what they meant by certain things. The second 30 minutes will be devoted to question number 2. And question number 2 is, what advice would you give to an early career scientist who is just starting off in this incredibly broad topic of heliophysics, which, as we've seen, basically covers everything? So those are going to be our 2 questions. And we're going to start with question number 1, which is, where do you think the breakthroughs are likely to be, with Carl Schreiber, who was one of the original deans of the school. Carl, you have 4 minutes.
Thank you. And I have 4 topics, but I'll go through them fairly quickly. The first one I already touched on. I think that we are basically entering exoplanetary system evolution and habitability just because of the data. But I've already said that, so done with that one. The other 3,
Use the mic.
I am using the mic. It is, the light is on. Even closer. Okay, proximity. And I realized that the other 3 topics that I chose were really not what we're doing, but how we're doing it, if that's okay, because your question was ambiguous. How are we doing science? I hope that we are going to be really doing distributed, multi-point, multi-perspective system observing. And that's a lot of words together, but we are in a state that we can fly very powerful instruments to all places around the solar system if we set our minds to it. We can integrate all that data if we set our mind to it. Because we're looking at a system, we might as well look at the system. Second is, we're going to have enormous support from computational infrastructures to complement what we cannot measure directly. So we'll have to learn, you will have to learn about data assimilation, data insertion, real-world modeling based on limited data. And the further you go away from the Earth, the harder it is, because the fewer data points we actually have available. But we don't know the system until we can visualize it, and we can't do it based on data alone. And the last point is, and even if you had the data, boy, the instruments we build nowadays are so powerful, they collect more data than we can bring down. Now, this has been true for a long time, but by now it's factors of 100, 1,000 or more. So we have to learn to bring data down that's interesting. And I don't care how you do it, but you have to start thinking about this. You can either have autonomous systems decide, which is tricky. You can send a preview down and do it. But somehow you have to bring your analysis tool to the data, because you can't bring the data to the analysis tool anymore. So you go and send your analysis software to an archive, or you pre-screen what you send down from the spacecraft. This has to be done. And some of my peers will then say, but then you're throwing away data. Well, you're throwing away marginally useful data, but you're keeping really useful data.
Thank you very much. Perfectly on time. Our next panelist is currently with NPR. She's been one of their foreign correspondents, very foreign, in fact, all the way to Juneau. Fran Bagenal, a professor at the University of Colorado here in Boulder, and also a dean of the school. Fran, 4 minutes.
Okay, so I'm going to start with current, which is Juno, which is the mission that we just went into orbit around Jupiter, 4th of July, and we will be studying the dynamo, the magnetosphere, the aurora of the biggest planet with the strongest magnetic field in the solar system, and understanding that will tell us what we have to do next in the outer solar system. And I'm thinking Uranus and Neptune, absolutely. I saw that on lists, totally agree. Next generation, we have to go back to those weird and wonderful magnetospheres. Next, actually, in the plan is a mission to Europa, either JUICE from the European viewpoint or the Europa Clipper in the US. That is going to be important because it's a plasma interacting with an icy surface, so sputtering, very interesting physics at multi-phases, not just plasma, but also interactions with a solid, and interactions with an atmosphere, which are very important and interesting. So it gets more complicated quickly. But most important are the induction currents that tell us that Europa has an ocean and quite probably life. So I'll just say to Carl that no way you exoplanet people know what the heck you're talking about when you talk about the habitable zone, which they picked up from planetary scientists. And planetary scientists have moved on and are telling you it's not the canonical place, it's you need to go look at the moons, the icy moons of the giant planets, not what exoplanet people call the habitable zone.
I'm not an exoplanet person.
No time for rebuttal. Carry on.
Okay. Most important, future, flotilla of small satellites across the solar system. So this touches on what George was talking about, analyzing the whole system, trying to understand, separating out spatial and temporal variability, and that will also require onboard data processing. So I 100% agree with you, Carl. Onboard data processing is a really big deal. And we can talk about Pluto and how the difficulties of getting data back from across the solar system. So small sats, we're doing a lot with multiple sats at Earth, MMS, and Cluster, and Themis, and so on and so forth. But we need to think about going small. We've got CubeSats. University of Colorado has 2 student-built satellites that are operating around the Earth right now. We need to do more. So I want you, young heliophysicists, to think about, I want you to design, build, operate, and do science with small sats across the solar system. There are all sorts of interesting targets. Venus and Mars, interaction of solar wind with these atmospheres, sending multiple spacecraft throughout the giant planet magnetospheres, going to comets, to asteroids, to counterpart objects. Let's think about how to build multiple small satellites, how to propel them, how to power them, how to get the data back, and it will require onboard data processing, so you're right.
Thank you very much. Our next panelist is the author of the award-winning chapter in Volume 4 called The Climate of Terrestrial Planets. David Brain is a professor at the University of Colorado. He's trying to figure out how to hold a meeting for 500 people in Boulder. So if you have any ideas on that, let him know later. David, 4 minutes.
Okay, thank you. So you heard a snippet about me right there, and I'll say that all my responses are colored by my own research experience. I consider myself to be a planetary space physicist. So I touch both the heliophysics community and the planetary community, and what especially interests me is the escape of atmospheres of planets, most particularly Mars, but also Venus and the Earth and other objects. So there are lots of interesting problems in the next 10 years that will be tackled in reconnection and how the solar wind is formed and in solar physics and in the solar atmosphere. I'm not going to talk about any of those. But I have 4 main categories. Number 1, missions that you might see percolating up in the next 10 years. Certainly not complete, but starting. And 10 years is a really short amount of time. So the type of things that you're going to hear more and more about are, first of all, CubeSat measurements, because they're cheap and small. And as soon as people figure out how to make CubeSats work in a constellation similar to Earth magnetosphere missions like Themis or Cluster or Artemis, you're going to see those even happening at other planets like Mars or Venus, and it would be great to be involved. And Jupiter. And Fran was kind enough to mention Venus and Mars in her comments, so I will also mention Jupiter in mine. Okay, next, more multi-planet missions or inner heliosphere missions or full heliosphere missions. Currently, those kinds of measurements and those kinds of papers are made and written, but they mostly happen by happenstance, using different platforms at different places that weren't really designed to work together. You'll see more coordination there. And finally, for missions, I think you'll see a rise of international missions. Those have been going on for years and decades, but I think you'll start to see a lot more coordination, considering both how other space agencies have maybe progressed and also the budget limitations. This year alone, and I'm not a special example, but I've been in India, and earlier today I was talking with people from the United Arab Emirates, so you'll see a lot of international collaboration. What about observations? Maybe you'll see, also an ice giant mission to Uranus and Neptune. That'll be great. Observations, I think there'll be better detections of atmospheric escape for exoplanets. Right now, exoplanet, it's a really primitive field for measuring atmospheric escape from exoplanets. Everything is hydrodynamic escape, the most extreme type of escape that you have. There are many other escape processes, and many exoplanet people, to be perfectly honest, have never heard of them. And you'll start seeing observations for those. I also think there'll be an incontrovertible detection of intrinsic magnetic field on an exoplanet. People have so far claimed to detect them on exoplanets. I think those claims are certainly worth arguing. I think everybody will agree within the next 10 years that we know about magnetic fields on exoplanets.
What's the current limit in Gauss? Do you know?
No, I don't. No. Okay, so that was missions and observations. Third category is models. Those are progressing greatly. I think we'll be able to model accurately atmospheric escape from a strongly magnetized planet such as Earth. It might surprise you to know that we currently really can't do that in a global sense. We can model different pieces of the puzzle, but we can't stitch them all together in one model. Also, I think that we will find or be able to model both an unmagnetized planet and a magnetized planet using the same modeling framework. We're nearly there right now, but because it's so hard when you have a strong magnetic field, your model comes grinding to a halt in that situation that I think we need to wait another 10 years for computer models to progress there. And finally, I think there'll be a determination of the role that magnetic fields play in limiting atmospheric escape from planets, which is really important for understanding habitability. The fourth category, in my negative 10 seconds left, is understanding. And I have 3 things there. So we'll have missions, we'll have observations, we'll have models, but what will we start understanding in the next 10 years? I think the understanding is going to come from more cross-body synthesis. Right now, planetary space physics, we send a mission to one planet, then we send a mission to another, then a mission to a third. I think there's very little integrative work that's being done right now, but we're primed for that in the next 10 years, comparing Venus to Mars to Earth. I also think there'll be better cross-pollination of the planetary science and heliophysics and astrophysics communities. That's already happening through exoplanets. That's the vehicle for the cross-pollination of those communities right now, and we're just still learning to speak each other's language. And finally, just a throw-off question, what has a stronger influence on atmospheres in our solar system today? Is it the quiet solar conditions, or is it the extreme events? We don't know the answer to that question, and I think we can in the next 10 years.
Great, thank you very much. Our fourth panelist, Professor Dana Longcope, has also been a dean of this school. He is famous for introducing concepts of topology into magnetohydrodynamics that certainly got many of us out of the field because we couldn't deal with topological concepts. But you're probably all very much well aware of them, and he's going to give you a completely different perspective on where future developments are likely to be. Dana.
Thank you, Tom. I have a lot to answer for then. I want to look at heliophysics, and it had traditionally been a collection of disparate subfields. And the subfields were defined culturally, but also by the kinds of physics dominating in one place. So to take an example, there were people working on the solar interior where magnetic field strengths are weak and can be ignored, where radiation is optically thick and you can treat it diffusively. There's the solar corona where the opposite is true. Magnetic fields are dominant, radiation is optically thin. At the boundaries between every one of these is a difficulty not just culturally but in physics, where these distinctions are no longer true. So the magnetic field is no longer weak or strong. It's kind of intermediate strength. These have proven to be the most difficult things to study. Unfortunately or fortunately, we have done a lot of work on each of the individual pieces, and what really remains is to start addressing these boundaries. So between those two places, for instance, is the solar photosphere and chromosphere, about which a lot less understanding is out there, and that is where we must go next. And we, fortunately, are building a telescope which will study in an exquisite detail structures in that very layer. But it's going to be a challenge. You're going to really have to bring to bear all the tools we've developed over decades. So that's a frontier is going to be understanding boundaries like that, and then between the corona, where we can ignore flows for the most part, and the solar wind where we can ignore the magnetic field. There is that region that so many of us like to put as a single conducting boundary at 2.5 solar radii. The solar wind either comes directly out of there or the corona just comes to an end there. We will have a mission, Solar Probe Plus, which in the 10-year time span will finally be making measurements not at that level, but so close to that level that we are going to have to deal with the fact that we're not in either regime, and we're going to have to roll up our sleeves and really come to grips with the physics. And I don't know if I will probably not be as active as any of you will be. So that is going to be your task, is going to be to come to terms with these interfaces between things. And only through understanding these interfaces and not just pointing at them and saying, yes, yes, that's hard, but really coming to understand them, can we synthesize the heliophysics, the whole broad area, into a single system that we can make space weather forecasts about and understand it as a system. So, and those are two missions that really will, mission or facilities, that really will in 10 years be sort of entering their heyday. So I think we'll have the tools to do this, we'll have the great minds to do this, and we have the need.
Great, thank you, Dana. And our final panelist for this first question is Amitabha Bhattacharjee, a professor out at the Princeton Plasma Physics Laboratory. And he is, his claim to fame, for those of you who don't know it, is he is probably the last human who knows everything about plasma physics. So he is a Renaissance scholar in that his work is touched on a variety of settings, not just within heliophysics, but certainly within laboratory plasmas, from very abstruse parts of plasma kinetic theory to fundamental questions in MHD. So, Amitabha?
Quite a setup, bound to fail now. A lot of really useful things have been said, so I'm going last and I'll not try to touch upon any of those. Certainly, this is an observationally driven discipline, and much of what we learn in this, we have to admit grudgingly as theorists, stimulated by observers. If we are not Eugene Parker, that is, who did predict the solar wind. So my vantage point is that of a theoretical plasma physicist, and I would like not to make any apologies about that. So if you would find my remarks a little too provincial from the point of view of theory, please forgive me ahead of time. In wandering from subfields to subfields, the thing that I have appreciated time and again is the importance of learning the basics of plasma physics. This is the discipline that underlies everything we do in heliophysics. I dare say even in astrophysics, where the astrophysicists tried to think that the universe was made of gas, referred to plasmas as gas for the longest period of time, till they realized how important magnetic fields can be. Heliophysicists, on the other hand, have appreciated the value of magnetic fields for quite some time, and in that sense, they have been much closer to plasma physics as a discipline than astrophysics has been. Certainly, the marriage of plasma physics and astrophysics is bringing brand new insights into astrophysics in a way that I think has the promise of changing astrophysics in very fundamental ways. The place where I teach, this is happening greatly now, and never has it been as good as it's been today. So there's a lot in terms of trying to learn plasma physics that I cannot speak enough of. The reason I emphasize foundations is without foundations, at worst, subjects can become like stamp collecting. And you would want to avoid that as much as possible. So the investments you make in learning basic plasma physics and mathematics are really worthwhile, and I address this comment to theorists and experimentalists alike. Because if you don't do this now, it'll be harder to do this later. Don't take the easy way out if you possibly can. Now, moving on to things that I think are really important, this is a very parochial view of what I think would become raging problems. Take, for example, the dynamo problem. Why is the universe magnetized? This is a great, great problem, as yet unsolved, with its manifestations in planetary dynamos, the solar dynamo, the astrophysical dynamos. There's some underlying principles that we have to go after in all of these things. And there's a commonality to the questions. The manifestations are different, but the questions are very similar. I can always talk about the importance of learning the fundamentals of turbulence or of three-dimensional reconnection. I'm surprised that Dana didn't dwell on this as one of his favorite subjects, and one in which there are very many open questions. Leaving aside those, I think that when we were talking about 10 years into the future, I was thinking that 2026 is not that far away. It's amazing how quickly 10 years pass. In 2023, you will have the world's first exascale computer in the US. And why is this so important? Because space weather is terribly important in the life of this discipline. It's not a perfect game. It never was, as George Sisko pointed out many years ago in an interesting article. But it is the main game we have. In order to play this game well, we have to go beyond our present-day computational capabilities. And why we have to start thinking about it now is that if you look at the computer architecture of the machines that are going to come online in 2023, our codes are not ideally set up to run on those machines. It seems to me that we are not asking those questions as searchingly as some other communities in physics are. And to our detriment, it's already been pointed out that SDO, MMS have provided data of far greater detail than our best computer codes can do. It'll always be a game that we'll be catching up on. Nature will always be a step ahead. But we really have to give serious thought on the computational end of the enterprise. Having mentioned that, I should tell you that one should not allow computers to dictate what science is about. So I hope that I come full circle and come back and say the theory, mathematics, has to be still important checkpoints for where our disciplines are heading. So it's a combination of all these three things that I hope will be our future, and you will be the leaders of it. Thank you.
Perfect. So not only are they erudite, but they actually can tell time because they each went 4 minutes. And so now it's your turn. You've been listening to all their visions of the future. What do you want to know about them?
Maybe my question is a bit off topic, but my question is related to the search for life in exoplanets. As far as I understand, we are looking for life in its primitive form, at least in the current stage. And observationally, we look for the signatures in the exoplanet atmospheres. So how strong is the interaction between those primitive forms and the atmosphere of the exoplanets that we will be at some point of time able to probe them?
Well, that's your question to answer scientifically. But I will repeat my point, which is outside Earth, within our solar system, where are we most likely to find life? And it's in the icy moons around Jupiter, not in Mars, nor in any atmosphere. So I think the exoplanet people are barking up totally the wrong tree.
All right, someone want to take a different viewpoint here? Okay, all right.
I'd love to bark back.
Rebuttal.
No, it's a matter of how many are there out there. We don't know how many planets there are with life. For now, let's start with the premise there aren't terribly many. Yes, look at every promising location you can actually get to, but other than that, try to find signatures that are as accessible as possible. So if we think about, this planet has been here for about 4.5 billion years. How long have we been sending out radio signals to look for? Not very long. How long has there been oxygen in the planetary atmosphere? A lot longer. So start the simple way. Look for signatures like that. Even though life is very small, maybe that you don't need big, intelligent people to run around before you get oxygen. but it's a much more readily detectable signature, so you've got a bigger chance of initial success. And then you target for maybe somebody's actually sending out a radio signal.
David, you want to add anything?
Sure. I'll say one thing, and I won't look at Fran while I say it, and I'll look at your faces to see if she's hopping in her seat. But one thing that's important about what both of them said is first of all, look for places that are accessible to you. And on an exoplanet, it's pretty hard to get beneath an icy shell of a body. And so that's one reason that maybe a good place to start for exoplanets is looking at atmospheres and the possibility that there's life at the surface or above. In that case, it becomes a search for what are called biosignatures. And people in the exoplanet community today are talking about different biosignatures, basically chemicals in the atmosphere or combinations of things. And it's pretty clear to many people right now that there's going to be no smoking gun that's going to tell us that there's life of any form on a planet, from bacterial all the way to sending radio signals. Instead, what I think it's going to be is a combination of signatures. And, you know, in a certain group of people, I could look out and I could make predictions on how many people in the room have children. And I could do that without talking to any of you. And there are many different clues that I could take to try and make that determination. I could look for a wedding ring, which isn't a smoking gun that you have children, but for many people is a prerequisite. I could look for evidence of being a certain age. I could look for spaghetti stains on your clothes because of either the children or you being too exhausted to clean yourself up. These are all different individual signatures, and when taken in combination, they give you a certain probability of making a reliable prediction, and even then, there's a chance you're going to be wrong. And I think this is exactly how we'll proceed with exoplanets.
That was a great question. I went to see the Star Trek film last night, so my answer is it's life, Jim, but not as we know it. Do we have another question?
Yes. I did too. It was terrible.
Oh, really?
Yes.
Oh, that's interesting.
Why do you think life in other planets is going to be similar to what we have here? Why are you looking for traces of oxygen or anything related to Earth? Because we won't have situations like this in other planets or in other solar systems.
I'm going to go ahead and go first. The glib answer is a failure of imagination. But maybe a better answer is this is a really hard question to begin with. And so to make that question easier, we look for what we know and what we've experienced already. If we start opening up the parameters, then the parameter space becomes too large to make any progress whatsoever. And so the way that most people have chosen to start is to stick with what we know.
Yeah, to me, it wasn't a lack of imagination. It's really pragmatic. We don't know what life is, really. We have no other planet that we know it exists on. So at least start with the one thing that we know that we need, at least. If we can find it, maybe we can learn more about what life is in other situations.
Right, the adage is you look for your keys underneath the street light because at least there's light even though you drop them in the dark, right? Other questions? We got time for one more.
Got it.
Okay. Actually, I have two questions.
No, just one. Pick
just
the best one.
Okay.
Do an and
So, the most important question that I think we have to address is how to face the funding problems for the future.
Oh my gosh.
Because you have a lot of good ideas about it, of the projects, what are the scientific questions that we have to address, but we need the resources. And I think that, as Nick says, we, as a community, we need to reach the other people, know how to express our ideas to the people that make the decisions.
Can I answer that one?
Yes, Fran.
So I've been involved in some demographic studies of the astrophysics, of planetary science, and of space physics. And so I've been looking at the demographics of those fields, the profession. And it's very important, I think, to have those demographics and understand them. They're all available, and I can provide online where you can go find them. I would argue that the real issue is not that we're overproducing. A lot of people are saying we're overproducing students and postdocs. The pipeline, you know, people say you're producing too many. I disagree with that. What we need is a sustainable pipeline that has long-term careers, that helps people develop and see a long-term future career. It's not all going to be academic careers, and I'm very glad that you're going to have a career discussion tomorrow that will involve non-academic careers. Many, many people in the field of heliophysics go into non-academic careers, and they're fantastic and they're great. I know very few underemployed people with physics degrees, with heliophysics degrees, and with astrophysics degrees, right? They tend to go on and do good things and be well employed. But that's not always doing soft money supported research, which is tough, it's hard, okay? And we have an issue with funding. We have a major issue with funding, and there have to be some discussions about where the funding is going in terms of supporting people to develop long-term sustainable careers in research. And that is a big problem that we're not dealing with properly.
Just very quickly, because what I'm going to suggest we do actually is 4 words, go ahead.
4 words, because I'm pointing at Dr. Fisher. So what? Who cares? Market your own problem.
And your 4?
There is money, it's more than 4. There is a good funding, there is funding coming into this field. And if you were in other fields, you would envy us. We need to be sure we know how to use that effectively. And I think this discussion of small spacecraft, there's a way you can get by with $1 billion. I mean, yeah.
Just $1 billion. So what I'm going to suggest is that we take this topic into the break, because that was a really good question. You want to talk to Lika, you want to talk to Dick Fish, you want to talk to Michael Thompson. These are all people who have had a lot of experience thinking about how you take the science and make the case for the importance of that science and the funding. So it is really a key question, and we could have an entire afternoon devoted to that. Instead, we're going to move to question number 2, which is, if you were called upon to give advice to this crowd of incredibly intelligent and very capable early career scientists who are moving out and want to do something totally amazing in the next 10 years, what advice would you give them in terms of not necessarily the research they're doing, but how they do it? Because you've kind of talked about where the breakthroughs are. So let's talk about maybe what Andres and Neil told us earlier, maybe more of the kind of how do you manage your entire life portfolio. So we'll go in reverse order and start with Amitabha.
Thank you. Begin with an anecdote. A few years ago in Princeton University, I organized a 10-year future plan for the Living with a Star program, and Andre actually gave a talk. It was a very moving talk, talking about the excitement of heliophysics and yet the difficulties of the future ahead. I heard him today, and the very wall that he saw, he has broken through. So I'm very glad to see him and other people in the business, and glad to see that he stood here to tell you that there is light at the end of the tunnel. I was born quite a bit earlier, and I think I had it easier than many of you do. But I had it harder than people who came before me. That is the story of maturing science disciplines. It's something that we have to deal with. And I took several wrong turns in the road. This is a very forgiving country and culture where you can take wrong turns and still come out fine at the end of it. I'm testimony to that. So I do not have a lot to give you in the way of advice except to tell you things that I have found to be terribly important. One, that interdisciplinary work is extremely interesting and very difficult. Very difficult because you're trying to identify principles that you think cut across boundaries, but you also want to make sure that in every subfield that you enter, you leave a deep impact, which means learning by complete immersion what you set out to learn. And to do so for every discipline that you venture into is the work of a lifetime. Brace yourself for it. It's the funnest thing that you will do, and probably the best thing if you do if your heart is into it. The returns will come slowly but surely. That's one thing. Second, we all know this is a rat race and you have to publish a lot and that people often count. But if you ask me, I think that for one who has written one paper too many, that one should write fewer and better papers. Simple reason. People will read your papers if they think that they can learn something from you. And if they read too many papers from you that doesn't teach them things, then they'll stop reading your papers. Third, write good proposals. Writing a proposal is not like writing a paper. It's a rhetorical argument where you're trying to persuade somebody else to fund what you think is worth doing. It's a different kind of a training, but one that you would get better at. But make it a point to learn how you do this. And finally, learn to give good talks. People are too busy to read papers even, but they'll go read your papers if you give them a really nice talk, an exciting talk that gets their attention. These things have worked for me, not always as easily as I see them, and sometimes have taken years. I am no role model for anybody, but I can tell you that these strategies have worked. Thank you.
Thank you, that's wonderful. Dana?
So, I was going to just discuss the fact that when you're doing scientific research, you're addressing a question, and by the end of your graduate career, probably it's a question that is a very detailed question regarding a specific detail in some measurement or model. But it's important to really back up and not just learn to give the answers to questions that people will expect, but to question your own understanding to the point that you think there must be a simpler way of understanding things. And it's amazing how many people work on extremely complicated things and lose sight of that fact that there must be a simple explanation, and the details will give you a slightly more accurate answer. But too often we don't try to step back and say, what is the really simple explanation for this? And I will then encourage you, one way to make sure that you're not getting bogged down in details too quickly is to start moving into different areas. Because when you enter a new field, the first thing you want to do is understand it at the simplest level. If you've spent a long time in a field, you've gotten to be cynical about it, brainwashed, to think like everyone else does and to focus on those details the way everyone else has ended up doing. And if you are if you go in there and it's new to you, you're going to ask some very basic questions, and don't be afraid to think, boy, you know, the people who've been working on this, they know a lot about the details, but somehow they've missed trying to understand the answer to one of the most basic questions. You'll be amazed how many times that happens when you move into some new area and say, I think I'm going to try to understand this. So that's, of course, as scientists, we're always supposed to be questioning things, and not questioning just to try to undo everything, but just to try to say, do I really understand this? Do I understand this at a level that doesn't say, oh, it's complicated? That should be banned as an answer to any question for a scientist. It's not complicated fundamentally. There's probably some complications on top of basic answers. So go after those basic understandings.
Now, funding, that's complicated.
Yes.
David.
All right, thanks. So far you haven't heard the word heliophysics in this second half, or magnetic field, or reconnection, or anything. It's all been general advice on how to be a scientist, and I'll do the same thing. And you know, this is the part where we're all trying to bore into your souls with things that we wish we had understood earlier on. So I'll say a few things that are the same and a few that may be different. Number one, give good talks and write good papers. I think this is the number one biggest piece of advice that I would give. And the reason for that is a little bit what Amitabh said, but I also think that science without communication is pointless. If you don't learn to do these things well, then your science is yet less useful to other people. And an average or above average scientist who can explain what they did is more useful than a brilliant scientist who cannot. Number two, papers, while you should make sure that you write good papers, the young people that I encounter, and I include myself in the young group, tend to err on the side of writing fewer papers and taking longer to publish what they've done, and there's some sort of mental block with publishing. But I'll just remind you that papers are really the only thing that last from your career. So at some point, you have to sit down and buckle down and prioritize the paper or the chapter, because that's what's going to last for 50 years. So make sure you write it, and make sure you do a good job when you write it. Don't travel too much, or you'll never get research done. Don't travel too little, or people won't know who you are. So find a happy medium. And then the addendum there is, as long as your family situation permits it, add an extra half day or 1 day to every trip that you take and see the place that you've gone to. Number 4, don't take on too much too early. There's the urge to do that when you're young and enthusiastic. I can do it, I can do it, I can do it, I can do it, I can do it. And I'm living proof of somebody who did that. Not successfully, but I tried to do that. Don't take on too much too early. There's plenty of time to build gradually to a successful career. 2 more things. Number one, this is something that I've sort of recently come to realize, and I'm 12 years out of PhD right now. No, 14 years. I also can't subtract. 14 years out of PhD. All boats can be floated. And as you progress in the field, even though there's so many rich problems for everyone to be working on, invariably you find yourself working in the same area as someone else and coming up with competing ideas and feeling a little bit competitive. Get rid of that feeling. There's plenty of room for everybody to make contributions, and when you play nice with others, they play nice with you. So don't put yourself into the adversarial mindset early on. And then the last thing is do things to remind yourself about the big picture. Pick science that's going to get you out of bed in the morning, that you're excited to go to work and think about, but then also do things like outreach and communicating with the public that let you step back from the line plot that's on your computer screen and think about the context of what you're doing. Sometimes I've found that when I do that, my own research direction will shift slightly when I've had to communicate to another group.
Thank you. Fran?
I have 3 basic points. The first is I'm worried that we're losing deep thinking. We're not spending time where we're so absorbed in our reading, our writing, or working on a computer program where we suddenly thought, oh my golly, it's been 2 hours and I'm behind. I should have been somewhere else. And this is because of distractions. So turn off your phone, turn off your email, try and find 4 sessions per week of 2 hours where you are lost in your intellectual development of what you're doing. You know, it could be all sorts of things, but I worry about losing that. Service work. This is sort of a little bit along the lines of what, you know, I used to say this to Dave all the time. Say no. Learn to say no. Learn to say no. So the issue of when to say yes and how to say no is an important one. I've actually written advice blogs on it. And so you have to balance busy work with actually being productive. And that is hard. It's difficult and it changes with life. But what I do now is I have a rule, which is when someone asks me to do something, review a paper, give a talk, spend some time doing, you know, talking to a student or whatever it is, any service job, certainly when it comes to sitting on committees and so on, I wait 24 hours. And that allows you to decide, do I really want to do this? And if you really want to do it, what are you going to drop instead? And if you don't want to do it, then you can say, sorry, no, but here are 3 people that I think would be great to do it instead of me, okay? So, and then when you said no to a service job, you get a GTK. This is from Sarah Gibson, a gin, a tonic, and a kiss from your partner. Okay, 3rd point. Everybody's talked about papers and publications. They're key, they're very important. You should indeed plan your 3 papers per year and get them submitted. If you're a theorist, it might be a little lower. If you're a data analysis, it may be a little higher. Or, if the idea of writing 3 papers a year makes you groan or sigh or feel uncomfortable or unhappy, then go and find a non-academic career where it's not so important. There are plenty of other careers where you don't need to write papers. But if you're in the research business, you do need to write papers and give talks. But there are other things you can do that don't require writing papers. So you have to, this is the sort of crux, with several of us have mentioned this, because you're at the point where you're sort of having to make these decisions. And the writing paper is sort of, I think, the push and shove, where it comes and goes. Okay.
And the last word is Carl's.
Going on the same theme here, lots of very good thoughts. I'll package them slightly differently here and there with my personal, what stereo? Can I have all three of them? Never compromise your integrity, because you can lose it only once. That is your credibility. So don't bend the rules. You use your highest moral standards. The short-term gain that you might get does not weigh up against the long-term losses. We're supposed to be honest people. We are all honest people when we start, and we should keep it that way. Second has to do with give good talks, write good papers. I'd say respect your peers in the broadest sense of the word. When you give a talk, I'd like to say, don't give talks, give a performance. Give the best that you can, because that audience came out to see you, to hear you. And I think the worst thing you can say, even if you do it, just don't never say, but the worst thing you can say is, as I was creating my talk last night, because that means your work was much more important than the few hundred people that might be sitting there listening to you that came out through rain and storm and all that. So respect them. Respect them in your papers. Write good, readable papers. And you might be tempted occasionally, I've done this too, to write another paper on another flare, and they are important too, but try to give them content. You weigh the number of papers against the contents of the papers that you're writing. Do the same in meetings, by the way. When you disagree with someone, there's probably a reason that person is saying something that you disagree with. And it is more educational to learn why that is the case than to fight it immediately from the outset. Say no, yes, but be active in your community and for your community. It's a way for you to learn about other people and about other problems. It's a way for them to get to know you. It's a way to shape your funding future because you're helping nudge it. So when you get a chance to be on a review panel or an advisory committee or the NASA Advisory Committee, which you will have a chance for when you get into your 70s, if NASA's still around.
You're a female, Australia.
At times, do say yes, because you do have something to bring to that table, and the table brings a lot to you. And finally, this has to do with be ready to go into new areas, not only because that gives you a new perspective, but also because the landscape of the science will change during your career. The things you now think are important are going to drift, either scientifically, technologically, politically, funding-wise. So be ready to do that and start working on being ready to do that right now. And that means, yes, you do go to another meeting, and the meetings that I've always found most informative are the smallest. The ones where you almost sit around the table and almost everybody is new to the subject or new to each other, and you can open up and say, this is a naive question, because you're allowed to say that, or think it, or do it, but you don't do it in a large solar physics division or a planetary physics division meeting, but you can do this in these small round table things. They are the meetings that prepare you to go into another field or be aware of something new. Take those opportunities right from the start.
Wow. I think this is some of the most amazing advice I've heard put together. Luckily for us, they didn't take their advice because they all said yes when someone asked them to be on this committee. I'm going to use my chair's prerogative to emphasize two of the points, and they're all really, really good points. So I hope you listen really carefully, because distilled here was several lifetimes worth of real truths about what it means. The first one that I want to emphasize is something that Fran said. You need to make time every day, and maybe you can't get 4 sessions a week, but maybe it's 30 minutes, maybe it's when you're in the shower, maybe it's when you're walking your dog, but make time to think. Without a pad in front of you, without paper, without pencil, without a computer. make time to think. It's the most precious commodity you have, is that time to think. And the second one I want to emphasize is the idea of writing a paper or making a presentation as performance art. It is performance art. You are performing for an audience. And it's very important for you to believe in yourself and to believe in who you are and make eye contact with that audience. And I'll leave you with a funny story. As a young postdoc, I went to Europe and I had to give a talk at the ETH in Zurich, Switzerland. And I was, of course, scared out of my mind to talk at this august place where all kinds of famous physicists had been. And the solar physicist that had invited me, as soon as I began my talk, promptly fell asleep in the front row. And my heart sank because I had all these viewfoils in those days, right? Little things where I'd carefully put different colors for different particles and stuff like that. This was before we had the capacity of Microsoft and to create all these PowerPoint things. And I kind of almost lost my way at that point. And I was feeling kind of low when I saw up in the crowd, sort of in the third row, this very older looking, very Swiss gentleman. And his brow was furrowed. And as I was talking, he started nodding over some of the things I was saying. And so the more I talked, the more he nodded. The more he nodded, the more I gave the performance of my life to this crowd. I mean, I probably have never given a better talk since. And I ended my talk with, almost a flurry, bravado. The orchestra came up, put my last slide. My host woke up, stood up and said, "Tom, that was a great talk. Do we have any questions in the audience?" And a few people asked some questions. And everyone left, and it was time to go off and have lunch in the canteen, because it's what you normally do in Europe. So on the way out, I kind of said to my person who'd invited me there, I said, there was a gentleman here, and I described him because he had kind of almost like this green vest and looked like he had just come in from hunting or something like that, and and I described him, and at some point I said, who was that? And I was thinking, maybe Wolfgang Pauli's assistant, maybe his person worked with Einstein or something, and he thought for a second, he said, oh, Johann. Yes, well, Johann is a retired school teacher, and he comes to all of our colloquia, and he doesn't speak one word of English. So give the performance of your life, right? Any questions for our team up here? Yes.
Before you give a talk, do you practice or do you go for an extempore performance?
Oh, of course you practice.
In front of a mirror or how?
You need to practice in front of your colleagues. You need to give talks. You need to get your research group, when you're about to go and give a talk, you need to practice. I mean, before the AGU, doesn't everybody do practice talks in your research group? When you're about to go and do an interview talk, you have to go find someone who will listen to your interview talk. It doesn't work doing it in front of the mirror. You need an audience.
Yes, it does work also in front of the mirror.
Right.
And I think, really, I talked through the entire presentation once, if only to myself. At least one person heard it. And the most important part of it that I'll practice 10 times are the first 3 sentences. Because once you're over the first 3 sentences, you've seen your audience, you know the room, and it's so much easier to continue. If you stumble on the first 3, you're uncertain for the rest.
I agree. And in those first 3 sentences, look out at the audience. You've memorized your 3 or 4 sentences, and you're looking to the audience, and you're saying, and you're smiling, and you're standing strong, and you're saying blah, 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 and of course, this will happen next. Then you go to the next slide, then you can start pointing. But if you start your talk by going like this, right, everybody's going to fall asleep on the front row.
Maybe that's what I did wrong. I just wanted to add something, because I think this is I don't exactly practice as in a front of. I never do a practice in a front of group of people. I think there is some form of personal choice. You have to discover what works for you. So for me, for example, as I make the presentation and I run through it in my head, I never speak it up. I kind of like go through it in my head. For me, in particular, the most important thing is to really have a very clear idea of how I go from one slide to the next. So those are kind of like the things that I think, because that's generally what is going to make you stumble or is going to take away from you. If you know exactly what are the 3 words that you're going to use to go from one slide to the next, then the rest of the slide kind of falls through. Of course, it may be that for you what works is practicing, in which case you should do. But I guess overall, the important thing is to give talks. You very quickly will figure out what you like about what other people do, and what works for you, whether practicing in front of people, you ask friends, or whether you just in your mind do it, or whether, but it's a craft, right? So you find your own path to that craft. Especially, I think that for me, seeing other people talk, like go to talks, and that really gives me a lot of, and trying always to have fun with your talk, I don't know. I always try to do something little different every time and just have fun with the talk.
If it's not common for you to do a talk in your group before AG or something, make it happen. Just do it, persuade your supervisors, go in front of the group and do it. Because it's better to do it uncomfortably in the group first before you go out into the real world.
Also, the advice that I would give is when you're getting ready to prepare your talk, when you're creating your slides, tell a story. And this will do 2 things. It will make the talk more interesting for your audience, but it will also give you confidence when you're going through and telling the story. Start with a joke, kind of ease the tension between you and the audience by making people laugh, and the rest will just flow.
Yes, pick the right joke, though.
Can I add one thing? And treasure people who give you critique on your talk. Not the ones that say, great talk, because that's a zero content thing. But those people, whether they're your friends or your enemies, they're telling you something from which you can learn. The same, by the way, is true for your referee. Your referee is your best friend, even if he's your worst enemy, because it's the one person who you know really tried to read your paper. So value that comment. Use it, no matter whether you agree with it or not. Do something with it other than bad referee report.
We do have talk sessions within our group, but the thing was, why I asked this question was, I felt that the extempore would be a more natural way of expressing yourself in a talk, and probably the practice thing was sort of artificial thing. The other thing is making eye contact. Do you always look at one single person or the whole people at the same time? Because that is a difficult part of when you give a talk, right?
So I looked mostly at the people that were awake, and there was only that one guy.
If you want to make someone feel really uncomfortable, pick that one person to talk to.
No, I think the thing about the eye contact is that you shouldn't be just looking at your slides all the time.
Yep,
right?
I agree.
As long as you turn into your audience and talk to them, it doesn't really matter if you focus on one person or if you're wide, wonder. I never really remember where was I looking, in the sense that as long as you're not looking at the screen, I remember looking at someone at a moment and then another person, but sometimes people move or they nod your head and your eyes kind of like zone on them when you see movement in the audience. But it's really more like looking, like facing forward, not just kind of like with your mic here and you're looking at the screen.
Performance.
It's a performance. I totally agree with that. It's like playing music, actually. If you have ever played an instrument in front of a crowd, it's a very similar kind of thing, where you go through it, you will stumble. The important thing is to keep going and have an awesome ending, right? Like, it's really it's performance art. I totally agree with that statement.
Something unusual that works for me. Read a novel by a really good writer. Words are powerful. Selection of words to describe scientific content can be very helpful.
Can I just follow up? I mean, when I'm teaching to a class, I try and make eye contact with everyone to make sure everyone engages at some point during the talk. When I'm giving a professional talk, I start off doing that, and then I end up latching on to the people who are actively listening and looking back at me. 2 or 3 of you, you may know who you are already. I was looking at mostly as I was giving my comments during this panel. And very often I'll go up to at least one of those people at the end and thank them for listening. So that's a reminder to also be a good listener in addition to being a good speaker.
Hi. About the papers, do you consider, what do you consider better, to write more papers or better papers?
I think all of us have an answer for this.
All right, how many would come down with more? And in early career, early stage in your career, more? How many would say better?
There's a happy medium.
You know, I mean, you've got to do at least 1 to 2. I mean, less than 1 a year, you've got a problem.
Yeah.
Sure. Right? You know, more than 3, I would say, you know, you first author, you probably have a problem too, right? So that's the sort of what we're talking about here. 1 to 3 a year.
Our last question, Stan Salmon.
Well, since we're freely dispensing advice, I have one more that perhaps helps give better talks and also write better papers, and it's not directed at grad students or postdocs, it's directed at the entire audience. Learn how to make better pictures. Graphics.
Yeah.
Not just with readable text and colors that can be seen on a screen or in a printed material, but also graphs of the right thing, graphs of something interesting that will tell a message. There's so many bad graphics out there. There's no excuse because of all the powerful computers we have. So I would say start with excellent graphics for both papers and talks that tell a message.
Can I just say one comment that's sort of a generalization, but also goes to the pictures. The goal of a talk is not to impress the audience with how smart you are or how much work you did. The goal is to make them understand at the simplest possible level, and graphics can go a long way toward doing that.
Let's thank this panel. Final word from Lisa before we have our discussion, and you can ask them any more questions.
Thank you very much. I think the party will begin shortly. This was a fabulous 10-year anniversary, and I believe this has been taped. So the ones that have not been able to listen to the whole dialogue will be able to actually get that online. What I wanted to do, I just want to take a few minutes right now to recognize the, the core contributors for this 10 years effort of the summer school, and it's just a very small token of appreciation. And so this is going to essentially, as I said, the core members. So if you haven't received one, I just made it for the core contributors of the summer school over the last 10 years. And so this is a certificate of appreciation for Carl Schreiber, and I'll read the comment, the short description here, and I will not read it for anyone else later. Thank you for your valuable contributions and leadership to the Heliophysics Summer School. And we've talked about Living with a Star program. We talked quite a bit about the star, perhaps a little less about living with the star. And so this picture here is actually a picture, the red aurora. I mean, that is an aspect of living with the star and a beautiful manifestation of actually living with this star. So thank you very much. Another certificate of appreciation, George Sisko, without whom also the summer school would not have started. George. Fran Wegener. Dana Lonko. I'm sorry that, I have put Nick to work even for this moment, because he's absolutely been valuable. While not a dean, he plays a much larger role in this summer school, and for all your work and support with the students. To Nick. Jan Soika. As I mentioned, Jan with Carl has been two of the longest serving deans of the summer school. And their valuable effort, without which this wouldn't have been possible. Thank you very much. Absolutely. It's the living. Amitava Bhattacharjee, I think I'm the only one who can probably pronounce that name. Thank you so much for your service. And with that, I think I'd like to adjourn this 10-year anniversary, and I hope there is a party being set up for us out there. Thank you.
Thank you.